Welcome to the GCSE Maths A-Star Independent Learning Resource. This resource is for students who are taking the higher tier GCSE Maths exam. It's for those students who are confident on D, C and B topics and would like to access some A and A-Star topics. 8 topics have been chosen and selected into 4 areas. Our first topics are surds and bounds, followed by histograms, then an algebra section on quadratic equations and algebraic fractions. Our last topic is on shape, which includes vectors, sine and cosine rule, and area of a triangle. After each section, there will be a short assessment for you to complete, and within each section, there will be functional style questions for you to practice. Our first section on number. We have 2 parts. First, surds, and then bounds. In surds, we're going to be practicing multiplying and dividing surds, simplifying surds, adding and subtracting surds, and surd problems. Followed by bounds, where we'll be looking at defining the upper and lower bound, and also being able to add, subtract, multiply, and divide measures involving bounds. The square roots of most numbers cannot be found exactly. For example, the value of the square root of 3 cannot be written exactly as a fraction or a decimal. The value of the square root of 3 is actually an irrational number. It is often simpler and more mathematically accurate to leave in the square root sign. These numbers are called surds. Given what I've just said, the question I want you to look at is which of the following is not a surd? The square root of 2, root 6, root 9, or root 14. And I need you to explain why. 1 minute, off you go. So, if we look at the 4 numbers you've been given here, root 2, root 6, root 9, and root 14. 9 is the only number of those 4 which can actually be written out. The square root of 9 is equal to 3. 9 is a square number, and if you root it, you get 3, because 3 times 3 equals 9. However, all of these other numbers, if you type them into your calculator, you'll notice that you will not get a whole number out, an integer. You'll get a fraction or a decimal value. Therefore, each one of those numbers are actually surds. So when we're looking at surds, there's a number of rules that you need to be able to learn and apply when answering questions. Our first one is around multiplying. We're going to demonstrate this first by looking at 2 square numbers. So we're looking at the value of the square root of 16 multiplied the square root of 16. 16 is a square number, and we know that we can find that out exactly to be equal to 4. So 4 times 4 gives us 16. So here we can see our general rule here, the square root of anything, that's your a value, multiplied by the same square root, the square root of a, actually just gives you the value a. If we go back here and apply it here, we have the square root of 16 multiplied by the square root of 16, answer 16. So when we look here at a number which is a surd, we've got the 3 there, it cannot be written exactly. We don't know what the square root is exactly, but we actually know we can apply our rule here, and it simply equals 3. So if I give you another one there, the square root of 5 multiplied by the square root of 5 is going to be equal to 5 exactly. That's your first rule. Our second rule is expressed here. The square root of a number, any number, multiplied by the square root of b. It's a different number this time. And actually, if you just have the square root of a multiplied by the square root of b, it's the square root of ab. ab meaning a multiplied by b. The first number multiplied by the second number. Again, we're going to look at some square numbers to demonstrate this first. The square root of 4 is 2. So we have 3 multiplied by 2 being 6. If we go back and look at our rule here, it says that the first number multiplied by the second number, here, AB, 9 multiplied by 4 is 36. So if we then apply the rule, here we have the square root of 9 multiplied by the square root of 4. We simply multiply our 9 times 4, which gives us 36. The rule here says the square root of 9 multiplied by the square root of 4 is actually equal to the square root of the two numbers multiplied together, which is our 36. Our square root of 36, 6. Takes us back to our answer here. So this rule here, being demonstrated with square numbers, can you now apply that to our second example, the square root of 2 multiplied by the square root of 8. 1 minute, off you go. So here we have the square root of 2 multiplied by the square root of 8. We simply multiply our 2 and 8 together to get the square root of 16. 16 is a square number, so we can write that as 4. The square root of 16 is 4. 4 times 4 gives us 16. So we now have two rules that we can apply to multiplication problems. Before we move on, I just want you to look at this problem here. We can use these two rules backwards when simplifying calculations involving surds. So the ones we've already just practiced are going forwards, looking at our surds, multiplying them out. We can actually use that backwards when we're going to be looking at simplifying, which we'll see in a moment. But just now, if you have a look at this example, we have the square root of 20 is actually equal to the square root of 4, the square root of 5. 4 times 5 gives us 20, if we could see that rule working backwards. We can then simplify our 4 to 2, the square root of 4 is 2, and 5 is a surd, it's not a square number, so we leave that as the root of 5. You'll see those in a few examples we're about to do next. So next we're going to look at dividing surds. First thing I want you to do is using your calculator to find the value of the square root of 20 divided by the square root of 5. So just type that into calculator, and I want you to see what you notice about that answer. Okay, so once you put that into your calculator, you should have come out with the answer 2. The square root of 5 divided by the square root of 4 is 2. Thinking about where that's coming from, we can see that 2 comes from the square root of 4. Where does 4 come from with the numbers 20 and 5? You can see here that we've got another rule which says that the square root of your first number, a, divided by the square root of your second number, b, is actually just the square root of a divided by b. So we have here our first number 20 and our second number 5. That's like the a and that's like the b. So we have 20 divided by 5, and it's actually the square root of that. So the square root of 20 divided by 5, we know this 20 divided by 5 is 4. Square root of 4 is simply 2. And that demonstrates it there. So my next question is, what do you think the value of the square root of 18 divided by the square root of 2 will be, and why? Once you've had a think about that, I want you to see if you can find two other surds that follow this pattern. 2 minutes, off you go. So let's look at this one. What's special about the square root of 18 divided by the square root of 2? Well, following our rule that we have here, that's actually the square root of 18 divided by 2. 18 divided by 2 is 9, so the square root of 9 is equal to 3. In this case here, our number that we have in our square root is a square number, so we have an integer, a whole number. So another number that could follow that pattern is you're going to have a number that's a square number in here. So for example, we could have 25. The square root of 25 is 5. We then need, working backwards, two numbers, a divided by b, which is going to give us 25. So a simple one, we could have 100 divided by 4. 100 divided by 4 gives us our 25. What would the original question look like for that, working backwards again? Simply the square root of 100 divided by the square root of 4, written like this. So the activity for you to do now, on the left-hand side, you have 4 of the third rules, and I want you to match these with the results. 2 minutes, off you go. Our first rule we have here is the square root of a multiplied by the square root of a. A and a, the same number there. That was our first rule that's going to come out with simply a. Our example for square root of 3 multiplied by the square root of 3 is simply 3. Our next rule, we have three numbers that are the same, the square root of a multiplied by the square root of a multiplied by the square root of a. This here matches with our result on the end here. We have our two numbers multiplied by together, square root of 3 multiplied by the square root of 3, which we know is 3. Then we multiply by another square root of 3, and we simply write that as 3 root 3, as it's described here, a root a. No need for the multiplication sign. Our next rule is dividing. We have the square root of a divided by the square root of b. A and b are different numbers. And this was the last one we looked at here that's actually just equal to the square root of a divided by b. If we do an example of that, we have the square root of, say, 10 divided by the square root of 2, which is actually equal to the square root of 10 divided by 2, which is the square root of 5, our answer. Our last one is when we have two numbers multiplied by together, a and b, the square root of them, but they're different numbers here. And in this case, we multiply our two numbers together to give our square root. This is the one we can use backwards. Remember this one, the square root of 5, square root of 4, then multiplied together, two different numbers, is going to give us the square root of 20. And that can work in both directions. So there are 4 rules, and we're going to apply those now to some problems involving surd numbers. On your page now, you have 5 numbers which I want you to apply some of the surd rules to simplify. Off you go. So our first one, the square root of 6 multiplied by the square root of 6. Both of the numbers are the same. So this is our rule here, where we have the square root of a multiplied by the square root of a. So our answer is simply 6. Our second one, we have the square root of 15. This is one of these cases where we'd work backwards to have the square root of 5 multiplied by the square root of 3. 5 times 3 gives us our 15. Both of those numbers are not square numbers. Therefore, we leave in the square root sign and they're left as surds. Square root of 5, square root of 3. Our next one we've seen already, the square root of 20. Remember, the square root of 20 can be separated into the square root of 4 multiplied by the square root of 5. 4 is a square number in this case, so we can remove the square sign and leave with 2. 2 root 5. Our next example is the square root of 2 divided by 3, which can be split into the square root of 2 divided by the square root of 3. Again, both of these numbers are not square numbers, therefore they are left as surds, square root of 2 divided by the square root of 3. Our last example here is the square root of 4 divided by 5. Similarly, we can split that into the square root of 4 divided by the square root of 5. In this case, we have 4, which is a square number, so on the top we have 2 divided by the square root of 5. And that there is as simple as that number can go. 3 more for you to practice on the next page. 2 minutes, off you go. So if we look at the first one, we have the square root of 18 multiplied by the square root of 2. One step you might start with is actually multiplying our two numbers together. That's that rule where we have a and b. So 18 multiplied by 2 is 36. Square root of 36, 6. Another way you might look at this question is splitting your 18 into 2 and 9. We know that 18 is actually equal to 2 multiplied by 9. And then we have our extra square root here, 2 on the end, which is there. Looking at this now, we've got a square number in the middle there, the 9, which can just become 3. We have root 2 multiplied by root 2. That's that first rule we saw, a and a, both the numbers are the same, so it's simply 2. We then have 2 multiplied by 3, which gives us our 6. Exactly the same answer that we get from doing 18 multiplied by 2, square rooting it gives us 6. Either way is fine, as long as you come out with 6 at the end. We have a look at our next example. We have the square root of 32. Well, one way you might want to do that is the square root of 16 multiplied by the square root of 2. That's splitting your 32 in 2. We then have a square number, 16, which can simplify to 4. 2 is not a square number, therefore you keep it as a surd. Our last example here, we have the square root of 8 divided by the square root of 2. This is one of the dividing rules that we looked at. Here we have simply the square root of 4. That comes from the fact we can write this, the square root over 8 divided by 2. So here we do our division, 8 divided by 2, which is 4, which gives us the square root of 4, the square root of 4 being 2. We're now going to look at the following question together. We have something, that's our gap here, multiplied by the square root of 2 equaling 6. So, how are we getting this 6? Where is 6 coming from? Well, we know that the square root of 36 gives us the 6. And we have that equal to the square root of 2, that's our value here, multiplied by something. So this missing part here, we need to be able to get to the square root of 36. Well, our second rule for multiplying said that the square root of a multiplied by the square root of b is equal to the square root of ab multiplied by together. So here we have 2 multiplied by something gives us our 36. Using inverse operations, 36 divided by 2 is going to give us 18. 18 multiplied by 2, 36, square root it, 6. So here I've applied one of the rules and we've worked backwards. In the answer here, square root of 18. I'm going to give you 3 minutes now to have a look at the next 5 questions. Think about all of the rules we've looked at for multiplying and dividing and think about working backwards. Off you go. So let's look at the first one together. We have a multiplication. The square root of 27 multiplied by something is going to give us 9. 9 again. Where is the 9 coming from? Well, we know that the square root of 81, that's 9 times 9, is going to equal 9. We've got 27 in here. 27 multiplied by something is going to give us the square root of 81. Again, using inverse operations, 81 divided by 27 is going to give us 3. But it's not 3 because we're dealing with our surds rules, it's going to be root 3. That's for our first one. Our second one is our division here. So if we write it out again, we have the square root of 48 divided by something is going to give us 2. Where's the 2 coming from? Well, the 2 comes from the square root of 4. So this has got to be equal to 4. How can I make 4 the square root of 4 when I start with the square root of 48? I'm going to need to divide by the square root of 12. Our third one is also a division. We have something divided by the square root of 8 being equal to 3. Our 3 comes from the square root of 9. This time our missing value is in the numerator and our denominator is the square root of 8. Something divided by 8 is going to give us our root 9. So we have the root of something divided by the root of 8 is equal to the square root of 9. So we're going to look at here doing our inverse operation, 9 times by 8. 9 times 8 is 72. So up here we have 72 divided by 8, which is giving our 9. We're actually talking about the root 72 divided by root 8 equaling root 9. Our fourth example is also division. It comes out as 5. Square root of 5 is 25. The square root of something divided by 5 giving us 25 is going to be the square root of 125 divided by 5 gives us 25. And our last one here, we have 8. 8 comes from root 64. Where does 64 come from? Well, here we have root 32 multiplied by, must be 2. 2 times 32 gives us our 64. So we have root 32 multiplied by root 2 equaling root 64, which is 8. We're now going to look at simplifying surds. You're going to have to use some of the rules we've used already, in particular the multiplying rule. When we solve mathematical problems, we're often required to simplify surds by writing in the form a root b. The b part there cannot be simplified. Therefore, it stays with the root. The first one we're going to look at is simplifying root 50 by writing it in the form a root b. In this kind of question, our first step is to find the largest square number that divides into 50. You might want to write out your square numbers to help you. 1 times 1, 1, 2 times 2, 4, 3 times 3, 9, 16, 25, 36, 49, and you may carry on. In this example, we have 50, so we're looking at the square root of 50. So we're looking for the largest square number that divides into 50. Well, here we've got 49, no, 36, 25, this is the number. So when I say divide into 50, the largest square number, I'm looking for the number that divides in exactly. Okay, so two numbers that are integers. So we have 25. 25 divides into 50 2 times. So 2 times 25 gives us 50. So in this case, we would write that down. The square root of 25 multiplied by the square root of 2. Square root of 25 multiplied by the square root of 2 separated. 25 is a square number, so we can then actually write that out as 5. So we have 5 root 2. If we look back here, we have the form a root b. b is the number that cannot be divided any further. That's the 2, because it's not a square number. And then we have the 5 at the front there, the a. So for clarity of what I've just said, here there's a definition. A surd is written in its simplest form when the number under the square root sign does not contain any factors that are square numbers. And that's the case here with our number 2. So this is simply written 5 root 2. Let's now have a look at adding and subtracting surds. Surds can be added or subtracted if the number under the square root sign is the same. So let's look at our first one. We have 3 root 7, add 2 root 7. So we have 3 lots of root 7, add another 2 lots of root 7, and we simply have 5 lots of root 7. So it's quite similar to algebra. If we had 3x, add 2x, we're going to have 5x altogether. And we can add those together because here x and x are the same. But if they were different, so for example 3y add 2x, we're not going to be able to do anything there because we've got 2 different values there for y and x. They're different. So up here when we apply to surds, if we've got the root 7, add 2 root 7, we've got 2, the root 7 is in both of them, we can simply add them. Very often that's not the kind of question you're going to get. This is the kind of thing that you will be asked to do. Can you simplify the calculation root 27 add root 75? The numbers are different. In this kind of question, you're going to have to start by simplifying. So first off, we must simplify our root 27 and our root 75 by using our surd rules. If we split root 27, we can split it into root 9 and root 3. 3 times 9 gives us our 27. 75 can be split into root 25 multiplied by root 3. You can separate that number in a different way by dividing 3 by 15. But in that case, you are not finding the largest square number. So from our example before, you're going to get to the answer in a quicker way by actually finding the largest number, the largest square number. If we look at those two numbers, we can write them correctly, like that. And they simplify. The 3 comes from root 9. 9 is a square number, so it simplifies to 3. 3 root 3. That's in that same format we saw before, a root b. Our second number here, we have 25, a square number. Root 25 is equal to 5. Here now we have 3 lots of root 3 and 5 lots of root 3. So our number underneath the square root sign is the same, and we can simply add them. 8 lots of root 3, which is 8 root 3. We're now going to look at 2 more questions that involve simplifying. Our first one is a fraction, given as here. Our first bracket, 6 take away root 3. Our second bracket, 6 add root 3, all divided by root 36. Our first step in this kind of question is to multiply out our brackets at the top. Again, I mentioned before, this is a little bit like algebra. If you had brackets, 6 minus 3x, bracket 6 plus 3x, you would multiply them out using FOIL, using your smiley lines, using a grid. Either way is fine. It's the same with surds, but you're going to notice that some of the surd rules are going to apply here. So if we multiply out our top line, our numerator, our 2 brackets, we're going to have 4 terms. 36, take away 6 root 3, add 6 root 3, subtract root 3 root 3. You can then see immediately that there's some things here we can simplify. We can see here, that's a surd rule, and we can see here that we're actually adding 6 root 3 and then we're subtracting it. So actually they disappear. So our next step is to simplify, and we're left with 36, our number at the front here. Take away 3, our rule, root 3, same number, is going to just give us 3. Once we do that, we have 33 over root 33. Working backwards now, we know that 33 on its own is equal to root 33 multiplied by root 33. And then we can simplify. We have a root 33 on the bottom divided by a root 33 on the top, and we're just left with root 33 on its own. This is not a square number, therefore we leave it with the square root sign at the front and expressed as a surd. The next question I'd like you to have a go at first on your own is 2 brackets on the top again, divided by root 18. Our first bracket is 3 subtract root 2, and our second bracket is 2 add 3 root 2, divided by 18. So, first step, multiply out your brackets. Second step, multiply. You have 2 minutes, off you go. If we multiply out our bracket as our first step, we are left with this. 4 terms again, always 4 terms multiplying out. 6 subtract root 2, add 9 root 2, take away 3 root 2. Always try and write that out full length before you simplify. Sometimes you can see immediately, oh, I can simplify this term with this term. Just write it all out, then simplify as your next step. If we simplify, we can see here, our first term stays the same, 6 and 6. Our second term, we've left them as the same to start with, and just looked at this part at the end. 3 root 2. 2 and 2 under the same numbers under the root sign is just 2. So we have at the end here, minus 3 times 2, which we know is 6 there. On our next stage of simplifying, we then have 6, and then we can see that these subtract. So our first term at the beginning, which we multiplied out, which was 6, subtract 6, that goes, and we're left with our 2 surd terms in the middle. Negative 2 root 2, add 9 root 2. Make sure you do not miss that negative there. That's why I've popped it in red. You can see here it's there. Take off the 6, it's easily missed. So we have minus 2 root 2, add 9 is going to leave us with 7 root 2 over root 18. Still some more simplifying to do here. Now let's have a look at the denominator. We have root 18. We know that root 18 can be split into root 9 multiplied by root 2. Doing that, we can then simplify further. We have root 9 is a square number, 3. We then have 7 root 2 divided by 3 root 2. Top and bottom have a root 2, cancel, cancel, and we're left simply with 7 over 3. That's perfectly acceptable to leave your answer like that. If you want to, you can divide in how many 3's go into 7, 2, 1 left over, and 1/3. But this answer here is the correct answer. So the next part of surds we're going to look at is something called rationalising the denominator. When a fraction has a surd as a denominator, the number at the bottom, we usually rewrite it so that the denominator is a rational number. So that's one without a surd. And we call this process rationalising the denominator. So that's the number at the bottom. If it has a surd in, we try and rewrite it so that the number at the bottom is no longer a surd. We're going to use this example to demonstrate the process. 5 divided by root 2. So at the moment, the denominator, that's root 2, is not rational, it's irrational, there's a surd there. So what we're going to do, we're going to multiply the numerator and the denominator by the same number. And the value of the fraction is going to remain exactly the same. We know this from normal fractions. If we have 2 over 4, half, we multiply them by 2, we simply have 4 over 8. It's still a half. We divide, still a half. All of those fractions are equivalent by multiplying, provided we multiply the numerator and the denominator. So we're going to follow that process here. And we're going to multiply by root 2. So we're going to multiply our numerator and our denominator by root 2. If we do that, we know that our rule of surds, root 2 multiplied by root 2 is simply 2. It's gone. It's been rationalised. The denominator now does not have a surd in it. The numerator has a surd, but that's not a problem. The process is rationalising the denominator. So we have 5 multiplied by root 2 is simply 5 root 2. It says here, you might want to write down the notes on your page as well, multiply the numerator and the denominator by root 2 to make the numerator a whole number. We can see here, 2, integer, whole number, no surds. That now is rationalised. We're going to apply exactly the same process to the following question. Rationalise the denominator, 6 divided by 4, add root 11. So root 11 there, that's got in the denominator, we need to rationalise it, we need to remove that to make the denominator a rational number, whole numbers. So we are going to multiply both sides by 6, subtract root 11. If we multiply it by 6, add root 11, the root 11 is not going to disappear. So we have our first fraction, 5 divided by 6, add root 11 up here, multiplied by 6, subtract root 11. Remember, we must multiply the numerator and the denominator by exactly the same if we do not want to change the value of the fraction. We can then see here that we are going to multiply both sides and we're going to be able to remove the surd from the denominator and then rationalise them. We now have simply one fraction multiplied by another fraction. The normal rules of fractions are going to apply. We multiply our numerator and we multiply our denominator. By doing so, we have on our top the numerator 30 subtract 5 root 11. That comes from our 6 multiplied by our 5, 30, and our 5 multiplied by negative root 11. We have our bottom here, we have our brackets if we want to write them in to help. 6 plus root 11 multiplied by 6 subtract root 11 is going to leave us with 36 subtract 11. If you want to do that out fully, we have 6 times 6, 36. 6 multiplied by negative root 11 is negative 6 root 11. We then have root 11 positive multiplied by 6 is add 6 root 11. They're going to cancel out. And our last term is root 11 multiplied by root 11. One's positive, one's negative. Rules of negatives, negative 11. Our rule of surds, when we're multiplying the same value together, just leaves us with 11. So here we have 36, subtract 11. Simplifying, we have 25 on our denominator. Our denominator now is without a surd, therefore it's being rationalised. On the top, our numerator, we still have 30 subtract 5 root 11. That's as simple as this fraction can go. There's a surd in the numerator, that's not a problem. The denominator is without a surd, therefore the denominator has been rationalised. There's now one question for you to try on the next page. Rationalise the denominator, 8 divided by 4, subtract root 10. 2 minutes, off you go. So looking at this question together, we're going to start in exactly the same way. Our first step, multiply both sides by 4, add root 10. Remember, that sign in there is always going to be the opposite to what's actually in your question, because if you're going to remove the root 10, you need to have the cancelling. If we multiply that, we have this. Again, show the step that you're going through. We've got our first fraction multiplied the same thing to the numerator and the denominator. Multiply that out, you're going to have 32, add 8 root 10. Divided by our 4 terms here on the bottom, we can see 16, add 4 root 10, take away 4 root 10, cancel out. There, we have 10, 16, add, subtract 10. So we have here 16, subtract 10, it's going to leave us with 6 in the denominator. So if we look at the simplified form of that, we have 32, add 8 root 10, all divided by 6. The denominator is now 6, therefore it's been rationalised, there is no surd there, and our numerator cannot be simplified any further. So that's your final answer for rationalising the denominator. So let's look at some problems now involving surds. The following rectangle has been drawn on a centimetre grid. Using the given lengths to find the length y and the width x of the rectangle, find its perimeter and area in surd form. 3 minutes, off you go. So this question is actually an application of Pythagoras' theorem. You'll often find this in surd problems, that the question is not purely about surds, but you're going to have to apply some other areas of mathematics to solve the problems. If we look here, we're first asked to find the width and length. The width and length expressed as x and y. We can see on our rectangle here, we have x across here for the width and y for the length. Just looking at the width, we have this value here. We don't know what x is, but we do know that here and here we have values. And we're going to use those. Pythagoras' theorem states that the area of on the 2 shorter sides, so that's your 1 and your 3, your right angle is there, therefore this is your hypotenuse. The area on those sides is equal to the area on the hypotenuse. We don't know the area, but we know that the length is 1 here and the length here is 3. So we're going to find the areas here by squaring them. The square root of 3, add the square root of 1. Square root of 3 is 9, square root of 1 is 1. So actually it's the square root of 10. That's fine. We don't know what the square root of 10 is unless we type it into our calculator and get a decimal number, but we want it in surd form. Similarly, on our length, we have our 2 values, 6 and 2. We square them, we add them, and we get 40. So we get the square root of 40. Now, there's actually something you can do with this one to make it slightly simpler. We can split our 40, using our surd rules again, into 4 and 10. So we have the square root of 4 multiplied by the square root of 10. The 4 can then be simplified into 2 because the square root of 4 is 2, so we have 2 root 10 units, whatever they may be. We're not sure if it's centimetres, metres, so we write our units down. So here we have our length, and here we have our width. Look back at the question now. We need to find its perimeter and area in surd form. So the first one, if we look at, is the perimeter. The perimeter is all the sides added up, we know that. So it's a width and a width, a length and a length. So here we have root 10, which is a width, add 2 root 10, which is a length, add another root 10, add another 2 root 10. So all together, because the number under the square root sign is the same, we have 1, 2, 3, 4, 5, 6. So we have 6 root 10 units. The units are the same when we're doing with perimeter, it's just the lengths and widths added up, so it's still units, the same as whatever is for the width and the length. The next part we're asked is the area. Well, the area is the width times the length. We have our width as root 10 and our length as 2 root 10. Multiply that all together, we have 3 terms. 2 multiplied by root 10 multiplied by root 10. We can then see another surd rule. Root 10 multiplied by root 10, both the same numbers, so just 10. So we actually have 2 times 10, which is 20. So actually in our area, we don't have the square root sign anymore because it's simplified out. So we express our area as 20 units squared. So again, whatever the units might be, centimetre squared, metre squared, we know for area, it's always squared. So our last question for surds has been taken from an exam paper. A large rectangular piece of card is, brackets, root 5 add root 20 centimetres long and root 8 wide. A small rectangle, root 2 centimetres long and root 5 centimetres wide, is cut out of the piece of card, and you can see that in the diagram here. What you need to do is express the area of the card that is left as a percentage of the area of a large rectangle. You have 4 marks, therefore 4 minutes, off you go. So this question is an example of one of the function style questions I referred to at the beginning of the DVD. You have several steps you're going to have to go through applying different areas of mathematics, but fundamentally you need to know your rules of surds. Let's look at the first step. So the first thing you need to be able to do is to find the area of the large rectangle, take away the area of the small rectangle. So expressing everything in surds and not worrying about simplifying too much, we have here the square root of 8 multiplied by the root of 5 add the root of 20. And you can see that I've left the brackets in there to express the area of the large rectangle. Take away the area of the small rectangle, which is just root 2 multiplied by root 5. Once you've done that, you're going to have to multiply out the bracket. It's the same as you were multiplying brackets out in algebra. You take the term outside, which in this case is root 8, multiplied by root 5, and then you do root 8 multiplied by root 20. So the term outside the bracket is multiplied by everything inside the bracket. Once we've multiplied out the bracket, our next step is to be able to manipulate the surds to simplify. We're going to do this by applying our rules. So if we look here, our first step is to actually multiply out here our 8. If we can put the 8 into root 2 multiplied by root 4, because 8 is divisible by a square number, 4. If we have that square number, we can then remove the surd. We then have our 20, which we can split into 4 and 5, and again our 8 split into 2 and 4. And we have at the end here root 10. The root 10 comes from our 2 root 5, multiplying those together. This then simplifies to 2 root 10, add 4 root 10, subtract root 10. What we've got here now are 3 terms all expressed as root 10, which can then be simplified to 5 root 10. We've got 2, add 4 is 6, take away our remaining one, 5. This here, 5 root 10, is actually the remaining area. So that's this here, where we've done the area of the large rectangle, take away the area of the small rectangle. Our question is actually asking us, if we look at the question again, we're asked to express the area of the card that is left, we've just found that out, as a percentage of the area of the large rectangle. So we then need to place the area of the remaining part we've just found out, 5 root 10, divided by 6 root 10. This comes from this part here, which is the area of the large rectangle. But we're asked to express this as a percentage, so we're going to need to multiply by 100 for our percentage. We can then simplify this further into just simply 5 divided by 6. Our two roots cancel out. Root 10 divided by root 10, they cancel. And we're left here with 500 over 6. Again, that's fine, that's a percentage. You might want to write the percentage in, or you can divide your 6 into 500 to come out as a mixed number, or you can type into your calculator, or you can leave simply as 500 divided by 6. The next topic we're going to look at is upper and lower bounds. Upper and lower bounds, actually defining the bounds, is a B grade topic, but what we're going to look at is actually applying these to problems. So first off, we need to make sure everyone understands what an upper and lower bound is. This is simply applying the rules or conventions of rounding. If we look at the first example here, my friend's height is 146 centimetres to the nearest centimetre. That additional piece of information is going to allow you to define the upper and lower bound. It's sort of the limits within which your friend's height could be. So she might not actually be 146 centimetres exactly, maybe a little bit more, maybe a little bit less, but when you round it to the nearest centimetre, as said here, it actually is 146. So the most this could be before it was rounded down to 145 centimetres is 145.5. That's the lowest it could be. If she was that height, she would round up to 146. Similarly, if she was 145.6, she would also round up. 145.7, she would also round up. This value here is the one we're interested in, 145.5, and it is called the lower bound. The least this could be before being rounded up to 147 is 146.5, and that value is called the upper bound. So for the value of 146, we have the lower bound being 145.5 and the upper bound being 146.5. And we know that because we're dealing with the nearest centimetre. What I'd like you now to do is to have a look at the following questions. You're given various values and told what they've been rounded to. You need to define the upper and lower bound. You have 4 minutes, off you go. So I'm now going to reveal the answers on the screen, and I'd like you to check them against your work. Make sure you've paid close attention to what the number has been rounded to. Is it 1 decimal place, 2 decimal places, centimetre, integer, to check you've got the right answers here. So once we're able to define the bounds, we then need to be able to do operations with the bounds. We need to add, multiply, subtract, and divide. Here is a sheet for your reference, okay? You might want to look back at it when we do some of these questions. L means lower bound, U means upper bound. So for example, this one here says that if you're multiplying and you want to find the lower bound, you must multiply the lower bound by the lower bound. If you want to find the upper bound, you need to find the upper bound multiplied by the upper bound. And similarly for adding, subtracting and dividing. This is for reference to be used during this section. So if we look at adding measures to start with, the following triangle has sides of length 3 centimetres, 4 centimetres and 5 centimetres. The question is, what is the upper and lower bound for the perimeter? I'm going to give you 2 minutes, off you go. So if we're finding the lowest bound, we're looking for the lowest possible value each one of the lengths could be. They are rounded here to the nearest centimetre. So here, if you're looking at the lower bounds, you're going to have for 3, 2.5, for 4, 3.5, and for 5, 4.5. They are all the lower bounds of each one of the lengths. We add them up and we find the lower bound for the perimeter, which is 10.5 centimetres. The highest possible values, instead of 3, we're going to have 3.5, instead of 4, 4.5, 5, we're going to have 5.5. So if we add up our 3 lengths for the triangle, they're the upper bound lengths, we get given the upper bound perimeter, which is 13.5 centimetres. Let's look at another question that involves adding, but within a different context. The angles in the following diagram are rounded to the nearest degree, so that's the nearest whole number, the integer. We have a straight line and we have 3 angles, 35A, that's an unknown angle, and 78. The question is, what is the upper bound and lower bound for angle A? I'm going to give you 2 minutes to have a go and then we'll go through the question together. Off you go. So if we look at this question, first off, we're going to look at the lower bound. We have a straight line. We know that the angles on a straight line add up to 180 degrees. So all 3 of these angles add up to 180. If we want to find the lowest value A can be, we're going to have to subtract the higher bound, the upper bounds, away from 180. So here, instead of 35, we're going to have the upper bound for that angle, which is 35.5. Add the upper bound for the second angle, 78.5. Take that away from 180 and we have 66. So that's the lowest value A could be. So if we want to find the upper bound, we need to subtract from 180, 34.5 and 77.5. Both of those values there are the lower bounds. So if we want A to be the biggest value it possibly can be, we need to subtract the smallest value, the lower bounds, from the 180. And in this case, we get 68. That's the largest A could be. So A actually ranges from the upper and lower bound from 66 to 68. If we're multiplying measures, we need to think about it slightly differently. The dimensions of a small tile are given as 15 millimetres by 18 millimetres, and there's a small diagram to show dimensions on the actual rectangular shaped tile. Question is, calculate the upper and lower bound for the area. So that's where the multiplying comes in. We're going to be multiplying these 2 lengths together. If you look back at the reference sheet at the beginning, to multiply, if you want to find the upper bound, the biggest number, you're going to have to multiply your 2 upper bounds together, your 2 biggest numbers. And conversely, if you're finding the lower bound, you're going to be multiplying your 2 smallest numbers, the 2 lower bounds for your dimensions. So if we look first here, we can see that the lower bound length is 17.5. That's 18 millimetres, the lower bound 17.5. And the width is going to be 14.5. We multiply those together and we get an area of 253.75. I've included the units there, good practice, millimetres squared. If we look at the upper bound, we have our 2 values, 18.5 and 15.5. We multiply them together and we have 286.75 millimetres squared, and that is the upper bound area. So when we're dividing measures, we're going to think about it slightly differently. A boy runs 200 metres in a 27.8 seconds. So he's running 200 metres and it takes him 27.8 seconds. So we have 2 different measurements here, one for the length and one for the time. We're then provided with further information. The distance is given to the nearest metre and the time is given to the nearest tenth of a second. So that's going to affect how we find our upper and lower bound. The question is, what is his greatest possible average speed to 2 decimal places. Okay, so we're going to use our meters, our distance, and our time in seconds, upper and lower bounds. We need to choose which one to be able to then calculate the speed. So first off, let's work out the upper and lower bounds for both of them, for the distance and the time. That's also a good thing to do, because if you're unsure as to which one to pick when you're actually doing your calculation, you're still demonstrating to the examiner that you know how to find the upper and lower bound, even if you choose the wrong one for the calculation. So if we look at the upper bound for the distance, we have 200.5 metres. The lower bound, 199.5. And for time, 27.85 seconds. And for then the lower bound of time, 27.75 seconds. Now we need to choose which combination we need for the distance and the time. We also need to know how to calculate speed, which is something else you would have learnt. So we need the greatest possible speed. Speed is going to be distance divided by time. If we want the biggest number, we want the biggest number on the numerator divided by the smallest number. So we're going to have the upper bound divided by the lower bound, and you'll see that on your reference sheet as well. So here, we're going to have the upper distance divided by the lower time. Remember, speed is distance divided by time, and we want the biggest possible speed. So we're going to take the upper bound for the distance divided by the lower bound of the speed. So we select our two values from our calculations that we've already done. So it's this one, our upper bound, divided by a lower bound, and we hear with a calculator 7.23 metres per second, and that's our units for speed. So here we have found the upper bound of the distance by dividing the upper bound of distance divided by the lower bound for time to calculate the greatest possible speed. So we've now done some simple examples on the different operations involving upper and lower bounds. We're now going to look at two exam questions together where we're going to apply some of the same rules we've just seen in the previous examples. Our first question says, work out the upper and lower bound for the value of D. Give your answer correct to 2 decimal places. And we have a formula. D equals to 2.6k, 2.6 multiplied by k, divided by f squared sine x. Okay, so we have a number of different values in there. We have k, f and x, all of which we're going to have to decide whether we need to use the upper and lower bound. Here I've copied through the dividing, which is what we're going to have to do, dividing our 2.6k divided by f squared sine x, to be able to see if we want the upper and lower bound, which way we're going to have to be able to use them. So first off, before we go any further, what I want you to do is to work out the upper and lower bounds for f, k and x. 2 minutes, off you go. So to be able to find the upper and lower bounds, you're going to have to use the further information they give in the question. So f is correct to 1 decimal place, k is correct to 2 decimal places, and x is correct to the nearest integer. So using that information, our upper bounds we have for f 1.45, k 3.205, and x sine 30.5. We'll look at the sign together in a moment. Our lower bounds are next here, f 1.39, k 3.195, and x sine 29.5. Now, sine is a button you're going to press on your calculator to be able to get this. You might want to check whether sine 30.5 and sine 29.5 is actually the upper and lower bounds. So if you pop that into your calculator, you can get numerical values. So by checking, sine 30.5 is 0.507 and sine 29.5 is less than, so that's right, it's 0.492. So we can just check there that definitely gives us a lower number, because sometimes if there are values in front, it might actually change our number here. So I check that first. So we want to find the upper and lower bound by using what we know here. We have the lower bound is found by dividing the lowest number, the lower bound, divided by the upper bound. When we're doing the upper bound, it's the other way round. So we take the upper number, the biggest number, divided by the smallest number. If we do that in both the cases, we're going to have the following two calculations. So here, for our lower bound, we have our lower bound values at the top, divided by our upper bound values. Remember, the 2.6 is the same in both of them. 2.6 is fixed. It's not a value that you're going to change. So they stay the same, and here you type in your sign. You simply type that into your calculator and output an answer. Our lower bound will obviously be smaller than our upper bound. Our next question is about a circular disc being cut out of a rectangular piece of metal. You can see here from the diagram. The question is, calculate the maximum and minimum area left. They don't use the word upper and lower bounds. Similar to the question before we had about the running, it was to the greatest possible speed, okay? In these questions, you need to know that you're applying your knowledge of bounds. You're given some further information. The length of the rectangle is 12 centimetres and the width is 8 centimetres. The radius of the circle is 2 centimetres and all measurements are correct to the nearest centimetre. It says here further to take pi to be 3.14. So pi is fixed at 3.14, so that's not involved in the bounds calculations. What I want you now to do is to calculate the minimum and maximum area left. So that's when the circular disc is cut out of the rectangle. 2 minutes, off you go. So once again, in these types of questions, always write out, define your upper and lower bounds before you do the calculation. So you need to check here that you have the upper and lower bounds for the length, the width and the radius. And this is quite simple because all of them are correct to the nearest centimetre. So they're going to be 0.5 bigger or lower for the upper and lower bounds. Here, if we want to find the maximum, we're going to have the maximum area for the rectangle subtract the minimum area for the circle. And that's going to give us the biggest amount left over. So if we do that calculation, we're going to have the maximum for the rectangle. That means we need the upper bounds, 15.5 multiplied by 8.5. That's going to give our maximum area for the rectangle. Our second one is the minimum. We take the minimum area of the rectangle and we subtract the maximum area for the circle because we're looking for the smallest area left. And we have this calculation. You'll notice in both of them that the 3.14 stays the same. I mentioned that at the beginning, that it says in the question, take pi to be 3.14. That is not affected by the upper and lower bounds. We've now come to the end of the number section. You have 10 minutes to pause the video and take the number assessment. Good luck. So our next section is on data. The topic we will be covering is histograms. There are 3 elements to the histograms. We need to be able to calculate the frequency density, construct a histogram, and interpret a histogram. The first point, histograms are not bar charts. Why? Well, there's 4 really important reasons. Our first one is that the class intervals, that's along the x-axis, may not be the same. Our second reason is that actually on the y-axis we are plotting the frequency density. The third reason is that the area of the bars represent the frequency, not the height, which would be the case in a bar chart. And lastly, this is an A-star topic, so you will not find histograms on the foundation paper, but you will find them right at the end of the higher tier paper. If you look here, there's some further information provided for you. It says here that the frequency density is equal to the frequency divided by the width of the interval. The width of the interval is how big is the interval, okay? And here, this calculation is going to be able to show us the frequency density, which is going to give us the height of the bar, which we will plot on the y-axis. We can use this equation in different ways. We can find the frequency from it, from rearranging, and we can find the width of the interval by rearranging, and we're going to need that when we're interpreting the histograms. So let's have a look at a histogram question. Very often you are given a table with the intervals and with the frequency, and your first step is to be able to calculate the frequency density. So if you take your calculator, we're going to have to look here at our table for our time to get the class width and our frequency. We know from our equation, and this is something you're going to have to learn, is that the frequency density is equal to the frequency divided by the width of the interval. One thing you might want to start by doing is actually writing down the width of the interval next to it. So here our first interval goes from the time being greater than or equal to 95 and less than 100. So our interval is 5. Our second one is also 5. But remember, they might not be all the way through 5. They can be unequal. Our second one we see is 105 to 115. So here we have 10. Our next one we have 115 to 130. Bigger again, 15. And our last interval is 20. So if you write those down first, again you might want to label it CW, class width, and then you have our frequency. So to be able to find our frequency density, you're going to have a calculator for this. So we're going to have in 8 divided by 5 for our first frequency density, and we have 1.6. So here, enter the line answers on the lines to one decimal place. So 1.6 is perfect. Our next one, we have 5 divided by 5. Well, we know that's 1. No need to use a calculator. Our third one, we have 8, the frequency, divided by 10. 8 divided by 10, 0.8. Our next one, our frequency is 12 divided by 15. You might want to check that one on the calculator. 12 divided by 15 is also going to give us 0.8. And our last one, we have our frequency 2 divided by 20, which is going to give us 0.1. So here now we have our frequency densities. You'll notice they're quite small. They often are. So when you're doing your scale on your histogram, you have to be careful. So what we're going to need to be able to do now is to plot these onto the histogram. I'm going to give you 2 minutes. Off you go. So if you look up on the screen now, you will see the histogram. You will notice that across the x-axis, our bars have different widths. You'll notice on the y-axis that it is labelled frequency density, not frequency. So here is a completed histogram. You will normally receive 2 marks for completing your histogram and 2 marks for calculating the frequency density as you did on the previous page. We're now going to look at a table that's completed in a different way. You will notice that there are missing spaces in both the frequency density and the frequency column. So you're going to have to use the formula in different ways. We can rearrange the formula to give us frequency equals frequency density multiplied by class width, or width of interval. So if we want to find our frequency, which is missing in this column, here and here, we're going to multiply our frequency density, in this case 1.2, by our class width, which is 5. So 1.2 multiplied by 5 is going to give us 6 here. Our next frequency that is missing is down here. We have again 1.2, and we have our missing value here, which is an interval of 5. So our missing frequency is 6. At this stage, you might want to check back at the question. Often, the total of the frequency is given in the question. So if you added up your frequency column, you could check whether you got to the right answer and ensured that you hadn't made any mistakes along the way. We then have 2 missing values for our frequency density. This formula here needs to be rearranged to the one on our previous page to give us our frequency density equals the frequency 4 divided by our class width, which in this case is 10. 4 divided by 10, 0.4. And our further missing value here is calculated from 7 divided by our class width, which is 5, which is 1.4. So as this example demonstrates, you need to make sure you can use the formula when both frequency is at the front, frequency density, and interval. In our next question, you will notice that the histogram has already been drawn for you. However, on the x-axis, the scale is missing. You are also given an incomplete table. So we're going to have to work both with the information in the table and the information in the histogram to find the missing scale and the missing values in the table. So if we look first at the information we have, the first bar in the histogram represents 40 people. Okay, so the frequency of the first bar, as we can see in the first line of the table, is 40, and the frequency density is 1. That's the value here, halfway between 0 and 2. We need to find out the width and the class interval and the various other missing values. So we have our formula that we first used, which was frequency density is equal to frequency divided by class width. We then rearrange that to give us the value for frequency. So frequency is found by multiplying the frequency density with the class width. And the third way that this formula can be arranged is for class width, or interval. So class width is equal to the frequency divided by the frequency density. So each one of these is going to help us to be able to find our missing values, and we need to choose which one to use when, how to use the information from the histogram and the information given in the table. So we look at the first value missing in the table. We need to find the width of the interval, so the class width. And that's found by taking the frequency, in this case 40, divided by the frequency density, in this case 1. 40 divided by 1 is simply 40. So we can then use this information to actually find the scale out on the x-axis. We know that this value here is 140, so it goes up in 20s, 100, 120, 140, 160 here, so this one is 180. In 20s again, we have 200, 220, 240, 260. Our next one, 280, and our final value on the x-axis being 300. We can then use this information to put into the table. So if we look at our second row here, we have our frequency density of 4, which we can see here on the y-axis. And we have our interval of 40, 140 to 180. We can write that in here, 140 to 180. And the only one we're missing is actually the frequency. So if we want to find the frequency, we must multiply the frequency density, which is 4, multiply the class width, which is 40. So we have 4 multiplied by 40. 4 times 4 is 16, but 4 times 40 is 160. So the frequency there is 160. Our third value, we're missing the frequency density. We know that the class runs from 180 up to 260. And you can fill the other ones in now. So we have 260 to 280, and our final one, 280 to 300. Filling in the last remaining squares, we have here our frequency density, which we know frequency density is frequency, 480, divided by the interval, which is 80. Again, easy to use your calculator. 480 divided by 80 is going to give us 6. Our next value here, we have frequency density missing again. We have our frequency, 100, divided by our width, 20. No need to use a calculator. 5, 100 divided by 20. And our last one here, we're trying to find the class width. The class width is going to be the frequency, 60, divided by the frequency density. 60 divided by 3 is going to give us 20. Check that's the width, 280 to 300. Yes, 20. So here now what we've been able to do is by using some of the information that was given in the words, the histogram and the table to be able to find out the missing points. So the last thing you need to do is to do a question from the top on your own. So this is an exam question. The table shows information about the total times that 35 students spent using their mobile phones. The time is given in hours and we have a frequency. What you need to be able to do is draw a histogram to represent this information. You have 4 minutes, off you go. So our first step is to be able to calculate the frequency density. Again, frequency density is equal to frequency divided by class width. So you might like to add another column to your table. It won't always be provided for you. So just here, I'm going to write frequency density, FD. So I'm going to take the frequency divided by the class width. Now I'm not actually given the class width, I'm just given the intervals here. So I'm going to actually then have another column, class width. The first width is 0.5, it's half an hour. Our second one is also 0.5. Our third one is 1 hour, and our fourth interval is 2 hours. By writing those down, you know exactly what you're calculating. So our first frequency density is our frequency 8 divided by 0.5. 8 divided by 0.5 is 16. Our second is 7 divided by 0.5, which is 14. Our third value for frequency density is 11 divided by 1, which is just 11. And lastly, we have 9 divided by 2, which is 4.5. We then have our 4 values for our frequency density. That will normally get you 2 marks in the exam. You then need to plot this, but you have not been given a scale. So if we look at our y-axis, where we're going to plot our frequency density, because it's a histogram, we look to see how many squares we have. So here we have 3, 6, 7, 8, 9, 10. So this here gives us 10, 11, 12, 13, 14, 15, 16, well our maximum value for our frequency density is 16, 17, 18. It would make sense that we plotted every one. So here we have 2, 4, 6. Remember, if you're doing this with a pencil, you can make any corrections as you go along. 10, 12, 14, 16. That's a good scale because you've used most of the axis available to you instead of squishing it lower down the page. Immediately once you've done that, you're going to write on the value. So here we have frequency density, which is fine as frequency density. And then we're going to need to plot. At this point, you're going to use a ruler to make sure that it's nice and smooth, and you're going to be using a pencil. So if we take our first value, we have our frequency density is 16, and our width from 0 to a half, which is to there. So along to 16, I'm going to draw a line across with my ruler, and then down to 0.5. Our next value goes from 0.5 to 1, again, across, but this time it has a frequency density of 14. So I'm going to go from here, over to 14, and then down to 1. Again, you're using a ruler to make your line smooth, and a rubber. Our third interval runs from 1 to 2, as we can see here in the table, and it has a frequency density of 11. So at 11, we are run from here, across, and down to 2. Make sure it's straight. And lastly, our final run runs from 2 across to 4, and it has a height for the frequency density of 4.5. We can see 4 is here and 5 is here, so it's going to be halfway along. Again, using your ruler, and down to 4. So we now have our histogram drawn. As you can see, on the x-axis, our widths are unequal, and on the y-axis, we have plotted the frequency density which we've calculated. It's now time for you to take a short 10-minute assessment on the data section that we've just covered, which will be on histograms. Pause the video now, 10 minutes, off you go, good luck. Our third section is on algebra. We will be covering two really important topics. Firstly, solving quadratic equations. We will be using all three methods: factorisation, completing the square, and the use of the quadratic formula. We will then be looking at algebraic fractions, simplifying, all four operations, and also looking at equations involving algebraic fractions. First off, quadratic equations. If the highest power is x squared, an equation is quadratic. The basic form of a quadratic equation is shown here on the screen. A, B and C are numbers, positive or negative. X squared is a term that must be there if it's a quadratic, and it must be the highest power. So for example, if there was x cubed, that would no longer be a quadratic, it would be a cubic graph. So here we're looking at the highest power being x squared. So an example of a quadratic equation would be this: x squared plus 4x subtract 45 equals 0. We have the x squared and it's the highest power. We have b here, which is positive 4, and c, which is negative 45. So what we want to be able to do is to solve it. That means find the value for x. Now, if you think about your quadratic graph, we have two options. The quadratic graph positive is this way, and a quadratic graph negative is around here. You will see that it crosses the x-axis at 2 points, here and here, here and here. Therefore, there are two solutions to x. So when we're solving all of these equations, whether we're using factorisation, completing the square, or the formula, we're going to get two values for x, two solutions, okay? So one method we can do this, as I mentioned at the beginning, is by factorisation. Factorisation involves rearranging this equation here, this quadratic, into two brackets, which is going to have x plus something and x plus something else. And it's equal to 0. Now, if you multiplied out those brackets, which would be expanding the brackets, you would get back to the quadratic equation. That's one method of checking that your answer is correct. So what we need to be able to do, we need to be able to think of two integers that add together to make 4. 4 is the b, the part in the middle, the coefficient of x. So two integers that add together to make 4, but multiply together to make negative 45. So one of them is going to have to be positive and one of them is going to be negative, because we've got that negative 45 at the end, so that's the C. So we need to think of two numbers that multiply together to give 45, but add together to give 4. So our factors of 45 are 1 and 45, but also 9 and 5. So 9 times 5 gives 45. But we want one positive and one negative, because what we're looking at is negative 45, and we're going to have to make 4. So we must have 9 subtract 5. 9 positive, 5 negative. So these are our two values that are going to go here in our brackets. So we actually have x plus 9, that's our positive, and in our other bracket, x minus 5. X subtract 5. Equals 0. At this point, it's then really easy. If we've got 0 here, anything, we're going to have an answer, a solution of 0, and we've got two numbers multiplied together. One of them's got to be 0. So what we do is we make our first bracket, x plus 9, equal to 0, and our second bracket, x subtract 5, equal to 0. If we have x plus 9 equals 0, we know that x must be negative 9. Negative 9 add positive 9 is going to give us our 0. That's our first solution. And secondly, we have x subtract 5 equals 0. Simple equation, x equals 5. So here we have our two solutions, x equals negative 9 and x equals 5. This method that's just been demonstrated here is called factorisation. Let's look at another example together. Here we have the equation x squared plus 6x plus 8 equals 0. It's a quadratic because our highest power is x squared. We have a being 1, b being 6, and c being 8. So by factorisation, we need two brackets. We write our brackets in, they are going to be equal to 0. We have x and we have x. Now our two numbers that are going to go after our x must multiply to give 8, but add to give 6. So if we think about the factors of 8, we have 1 and 8, 1 times 8, 2 and 4, and none others. There's only 4 factors of 8, and we need to make 6. So with 1 and 8, we're not going to be able to make 6, but with 2 and 4, we add them together to make 6. So both of our numbers in this case are positive. So we have add 2, add 4. Doesn't matter which way round you do it. Now if you multiply out that bracket, you're going to get back to the original equation. X squared plus 6x plus 8 equals 0. Remember last time, we need to make both of these brackets equal to 0 separately. So we have x plus 2 equals 0 and x plus 4 equals 0. So x must equal negative 2, and here x equals negative 4. So there are two solutions for x for this equation using factorisation. If you look on the next page, there's 3 more quadratic equations for you to factorise. You have 4 minutes, off you go. So, looking at these 3, our solutions are as follows. To the first one, x equals negative 3 or positive 5. Our second, x equals negative 3 or x equals negative 4. Both negative solutions. And here we have x equals negative 6 or x equals 1. The next example, you'll notice that the coefficient of x squared is not 1. We have, in this case, 3. 3x squared, subtract x, subtract 2 equals 0. In this example, we think about it in the same way. We're still going to have two brackets being equal to 0. But our first step is slightly different. We're going to multiply the coefficient of x squared, which is the a value, by c. So a multiplied by c is going to give us negative 6. We think about the factors of 6. We know it's 1 and 6, 2 and 3. Similarly, we're looking for the numbers that are going to match our b value here, which is negative 1. So this is no good. However, here with our 3 and our 2, we will be able to make negative 1. So what we're going to do, we're going to rewrite this with our two terms in the middle. Our first term is 3x squared. We're then going to be replacing our middle term here, minus x, with our two new terms that we've created here. We need minus 1, so this one will be positive, and this one will be negative. So we have plus 2x, take away 3x, take away 2 equals 0. So what we've done there, our first term stays the same, 3x squared. Our last term stays the same, negative 2. In the middle here, instead of thinking it as our 2 and our 3, we've actually replaced this with positive 2x, take away 3x, which is the same as negative x. We can then factorise separately the first two terms and the second two terms. So if we look at our first two terms, our common factor is x, which goes outside the bracket. Then we have 3x plus 2. Close our bracket. We then look at our second two terms. We've got negative 3x, negative 2. So the only factor that's common to both of those is negative 1. Inside the bracket, 3x plus 2. This part is essential. If both your brackets are not the same, you would have made a mistake earlier on. So we've got this bracket and this bracket the same. We then have our two terms that we factorised, x and minus 1, which forms our first bracket. Our second bracket, 3x plus 2 equals 0. Then we're in the same situation we were before, with two brackets being equal to 0. We do the same as before, make each bracket equal to 0. So we have x minus 1 equals 0, x equals 1. And our second bracket, 3x plus 2 equals 0. Remove the 2, so we have 3x equals negative 2. So x is equal to negative 2 divided by 3. Our two solutions for x is 1, x is negative 2 over 3, 2/3. On the next page is one of these for you to try. Here we have 2x squared, add 5x, add 2 equals 0. The coefficient of x squared is not 1. Apply the same rules on the previous example. 2 minutes, off you go. So let's have a look at this together. 2 times 2 is going to give us 4. The factors of 4, 1 and 4, 2 and 2. We need to make 5x in the middle here. So this is no good, this is what we're going to be looking at. If we need 5x, both of those are going to have to be positive. So we have our first term, 2x squared. And remember, we're rewriting, we haven't done any factorisation yet, we're rewriting that middle term, 5x, as two separate terms, 4x and 1x, plus x, plus 4x, plus 2 equals 0. So again, we haven't factorised, we've simply rewritten the middle term, 5x, as x plus 4x. We're then going to factorise our first two terms, then our second two terms. So we look at our first two terms, the only thing that's common to both of them is x. So we put x outside the bracket, inside 2x plus 1. Our second two terms, we have 4x plus 2. Our common factor is 2. So we add 2, it's positive, bracket, 2x plus 1 equals 0. Remember from our previous example that we must check whether the terms inside the brackets are identical. In both brackets we have 2x plus 1, so we know we're on the right track. Our next step is to get our two terms that we factorise that were outside, x and 2 together. So we have our first bracket, x plus 2, and our second bracket, 2x plus 1 equals 0. Then we need to find our two solutions. So our first bracket, x plus 2 equals 0. So x equals negative 2. And our second bracket, 2x plus 1 equals 0. Step 1, 2x equals negative 1. Step 2, divide through by 2. X equals negative 1 over 2. Which is negative a half. So our two solutions, we have x equals minus 2 and x equals minus a half. So our second method we're going to look at together is called completing the square. And it's another method to solve quadratic equations. There's two steps to it. The first one, you must divide the coefficient, that's the number in front of x, by 2. So whatever that number is, you divide by 2. And that's the number that goes inside the bracket with x, and that's your squared bracket. You then need to compare the constant with the constant in the equation, and then we adjust. Okay, so the first two steps, and then we solve as normal. We have our two brackets being equal to 0. So that first step is really important by dividing the coefficient of x by 2. So the example we're going to look at together is x squared, add 8x, add 12, equals 0. Our first step we're going to follow as described above. We're going to divide the coefficient of x by 2. So we have 8 divided by 2 is 4. Write it down. You let the examiner know exactly what you're doing. That number goes inside the bracket with x. So we have x plus 4 and we square it. That's our term there that's going to be squared. We then multiply out that bracket. So if we have x plus 4 squared, it's x plus 4 multiplied by x plus 4. We're going to have three terms as a quadratic. We're going to have x squared plus 8x plus 16. If you're not confident with multiplying out the brackets, remember you can always use a grid where you have your x plus 4, your first bracket, your second bracket, x plus 4, and multiply out to get your four terms. I'll show you in this example. So we have x squared, 4x, it's all positive because there's no negative terms, 4x, and then 16. Remember, multiplying those two numbers together, 4 times 4, 16. And then we get 8 by adding those together and simplifying. So that's where our x squared plus 8x plus 16 comes from. We then need to compare this constant with the constant in the equation. So if we look here, x squared is the same, 8x is the same, but we've got 12. We want 12 and we've actually been given 16 in this case. So if we look at the next step, when we're comparing across these, we're going to take away our 16 and add our 12. So the difference there is actually 4, negative 4, because we've got 12 in the equation we've been given, and when we've done our working out, we've got 16. We don't want 16, we need 12, so we're going to subtract 4. So that's where this line here we have. If we look here, we have our term in the brackets, so we have x plus 4. The 4 came from dividing that coefficient of 8. That's all squared. And then we take away 4, because we got 16, we didn't want 16, we wanted 12. And that's equal to 0. Then we can rearrange that to get x plus 4 squared equals 4. And then we're going to solve to find x. This is just like solving equations. So the first thing we need to remove is the power. So if we have x plus 4 to the power 2 equals 4, and that's what we're going to remove, this power to start with. If we have anything to the square, the inverse operation, so like multiplying the inversions, dividing, for this, it's square rooting. When we square root a number, there's two possible solutions. So if we square root 16, we can get positive 4 or negative 4. Remember, two negatives make a positive. So in this case, we can have 4 times 4 equals 16, or we can have negative 4 multiplied by negative 4 equals 16. So when we have a square root, we must have a positive and a negative solution. So our first solution, we have x plus 4 equals 2. So in this case, x equals negative 2. Our second solution, x plus 4 equals negative 2, remember that from the square root, take away 4, we have x equals negative 6. So there are two solutions from this quadratic by completing the square. If you look on your next page, you have the equation x squared plus 12x take away 5. The first step is to complete the square, and the second step is to be able to solve this. I'm going to give you 4 minutes to have a go on your own, and then we'll go through it together. Off you go. Let's have a look at this question. If you look up on the screen here, I've revealed the working out. Let's go through it together. We have here, compare this expression to x plus 6. Our 6 came from taking our 12 and dividing by 2. We put that in the bracket, the squared bracket, with x. So we have x plus 6 all squared. Multiply out that bracket like we did before, and we get three terms. X squared plus 12x plus 36. So if we compare this to our original equation, we can notice the difference. X squared is the same, plus 12x is the same, but we had minus 5, not 36. So we're on 36, we want negative 5, so we're going to have to subtract 41. From our 36, subtract 41 brings us to negative 5. That means it's the same then. So here is the completed square. Then, to be able to solve it, we make it equal to 0. So we have x plus 6, all squared in the bracket, subtract 41. We are going to move the 41 onto the left-hand side to have 41 equals x plus 6 all squared. So now, to solve for x, our first step is to square root 41. So we have x plus 6 is equal to the positive and negative of the square root of 41. So we're going to have two solutions. X equals the positive square root of 41, take away 6. And our second solution, x equals the negative square root of 41, take away 6 again. We simply put that into our calculator. So first off, the square root of 41, take away 6, that's the positive one, is equal to three significant figures, 0.403. Our second one, we're looking for the negative square root of 41. Take away a further 6, which is equal to negative 12.4 to three significant figures. So here again, we followed the same steps. Once we found out this bracket, x plus 6 squared minus 41, we rearranged to give us our 41, and then the key part is square rooting the 41 to give us the two solutions, the positive square root of 41 and the negative square root of 41. Subtract our 6 gets our x on our own, and we're left here with our two solutions for x. Sometimes, like with our last method of factorisation, the coefficient of x squared is not always 1. When the coefficient of x squared is not 1, quadratic equations in the form as we had before, ax squared plus bx plus c, can be rewritten in the form a outside the bracket, x plus p, all inside the bracket squared, plus q. So these new terms, p and q, are numbers that we are going to be able to find when we complete our square. The a we see is the same as in our original form of quadratic. It's the coefficient of x squared. So we remove that by factorising. So let's look at the example. 2x squared plus 8x plus 3. We start by factorising the first two terms by dividing by 2. 2 because 2 is the coefficient of x squared. If it was 3, we'd be dividing through by 3. If it was 4, we'd be dividing through by 4. So if we do that, 2 outside the bracket, then we have x squared plus 4x. The 4x is because we have the 2 outside the bracket now. 2 times 4x gets us back to our 8x. It's exactly the same. We've just put a bracket in, we factorised. Plus 3, the 3's on the end. Okay, now let's look at our next step. We then complete the square. So when we complete the square here, we have inside the bracket the 2. The 2 comes from the same reason as before, dividing the coefficient of x, that's 4, by 2. And putting it inside the squared bracket with the x. We have x plus 2 all squared. If we multiply out x plus 2, we are going to have x squared plus 4x plus 4. We started with x squared plus 4. Now the 3 we're not dealing with at the moment, okay? So we don't want that 4 there, so we're going to subtract the 4, so it's going to be 0, okay? So we have x plus 2 squared, subtract 4. Now remember, all of that has the 2 in front because we factorised at the very beginning by taking the 2 out. So our next stage here, we can see that our original equation that we started at the very beginning, 2x squared plus 8x plus 3, is equal to 2 that we removed at the beginning, we factorised. What we've just worked out by completing the square, shown here on the screen in purple, x plus 2 squared, take away 4. But that's all got the 2 in front, so that's where the extra bracket's there. Add 3, the 3 bit there is at the end. So then we're going to do some simplifying. So if you look here at the next line, we have 2 bracket x plus 2 squared minus 8 plus 3. The only thing that's changed there is that we multiplied our 2 outside by our -4. So 2 times -4 is -8. The 3 is the same, the bracket at the beginning is the same. And simply from then, at the end now, we've got -8 plus 3 is going to give us -5 at the end. Our term at the beginning, 2 stays there, our bracket, -5. So this here is completing the square for this quadratic that you've been given in the question. If you were then asked to solve it, you would have to make it equal to 0 and then rearrange and solve for x, which we'll be doing in further examples. So let's go through one of those examples again from the very beginning. This time we have a different equation. 5 plus 6x take away 3x squared. So the first thing we notice, the coefficient of the x squared is no longer 1. It's -3 in this case. So that's where our attention goes for the very first part. We need to factorise those two terms. So we're going to remove the -3. So as it says on the screen here, we start by factorising the terms containing x's by -3. -3 because it's the coefficient of x squared. Remember last time we factorised by 2 because that was the coefficient of x squared. So if we do that, we then have this. Our original, 5 plus 6x minus 3x squared. That's the original. 5, we're not dealing with the 5. We have not factorised the 5. It stays the same. We factorise by -3. That means we put -3 outside the bracket. And inside, we're then left with -2x because -3 multiplied by -2x is going to take us back to that positive 6x. And our last term here is positive x squared. We've removed our -3, so we've factorised by -3 and left our term here, x squared. We now have a quadratic here in the bracket when the coefficient of x squared is 1. There's nothing in front of that x squared, it's 1. What might be easier before you move on to completing the square is just to rearrange that, to put our positive term first, x squared, followed by our negative term, 2x. So here, we've just rearranged those so we have positive x squared, take away 2x. Everything else is exactly the same, so it's ready now to complete the square. We're going to follow the same process for completing the square, and what we must do is look at our term in front of the x. That's the coefficient of x, which is the b value, which is -2. We divide that by 2, like we have in all of the other completing squares, and we get -1. Divide that through by -1, and what we have here is our new bracket, x subtract 1, all squared. Take away 1. Where's the take away 1 come from? Let's have a look at this one again. X minus 1, all squared. You're going to square that. You're going to have x squared minus 2x plus 1. Plus 1 because we've got two negatives multiplied together. So here, we look back, x squared, yep, that's the same, minus 2x, yes, that's the same. 1, no, there was no 1 there to start with, so we need to subtract it. Remember, all of this has the -3 in front. There's a -3 in front of all of this completing the square. We're going to have to factor that in now. So if we look at our next stage of our working out, we have here all of our terms, x minus 1 squared, minus 1, all in a bracket. See there in the purple. And it's -3 in front. So we're going to get rid of the -3. So what we need to do now is to multiply our -3 by our -1. -3 multiplied by -1 is +3. That's where the +3 on the end comes from. The 5 is the same, the -3 stays in front of the bracket. We then have two terms we can simplify, 5 at the beginning and 3 at the end. So we actually have 8 altogether, take away 3 bracket x minus 1 squared. Again, that's completing the square for the quadratic expression here at the beginning, 5 plus 6x minus 3x squared. On our next page, we have a quadratic equation again, x squared plus 8x plus 5 equals 0. This time we're actually going to complete the square and solve. So, our first step, complete the square of the left-hand side. We divide our 8 by 2 and we get 4, minus our 16 plus our 5 equals 0, which comes through to 11. So altogether we have x plus 4 all squared, take away 11 equals 0. Rearrange for the 11 on the right-hand side. We have x plus 4 all squared equals 11. Our next step to square root our 11. And remember, we have that positive and negative solution. So x plus 4 equals the positive square root of 11 and the negative square root of 11. Again, we've got then the positive square root of 11, take away 4, and then the negative square root of 11, take away 4. Again, pop that into your calculator. 11 is not a square number. Therefore, you will get a decimal solution here, minus 0.683, correct to 3 decimal places. And the other solution is also negative 7.317. Our last example for completing the square is another quadratic. However, this time the coefficient of x squared is not 1. So complete the square and then solve for x. You have 4 minutes, off you go. Let's have a look at this question together. Our first step, as we can see here, is completing the square. We take the 2 outside. That's the coefficient of x squared. We need to remove the 2 by factorising. We then have x minus 1. The minus 1 comes from the point here that we took the 2 outside and we were left with x squared minus 2x. So now we're going to complete the square for our terms here in the bracket. The 2 remains. Open your big bracket. Here we have our first bracket, which is x minus 1 all squared. The minus 1 comes from our negative 2 here, the coefficient of x that we need to divide by 2. So negative 2 divided by 2 is negative 1. If we multiply out that bracket, we're going to have x squared minus 2x, exactly what we started with, but also a positive 1 term. The positive 1 comes from multiplying our negative 1 by negative 1. Positive 1 at the end here. Now, we didn't have a 1. Remember, we only had at the beginning x squared minus 2x. So we must subtract our 1 here. And then close our bracket. Remember, we started here by a positive 1. So there's a positive 1 at the end. By multiplying through by our 2, we have 2 bracket x minus 1 squared, take away 2, add 1. Remember the 1's on the end there. The 2 here, multiplied by negative 1 is your negative 2. And this part here simplifies to negative 1. Negative 2, add 1 is negative 1. So here, this is what we get from doing our working out here. So be really careful as to where that negative 1 comes from. Once we've got that, we can rearrange and solve for x. So let's have a look at the next step. We add 1 to both sides. So we then have on our left-hand side 2, open the bracket, x minus 1 squared equals 1. Our next step, divide both sides by 2. That removes the 2 in front of our x here, because it really says 2 multiplied by the bracket. So we divide the inverse operation, we have a half. We then have x plus 1 squared equals a half. Our next step, we're going to find the positive and the negative square root of a half, and we're going to add 1 to it. Our first one here, which is positive, we have 1 add the square root of a half, and on the other side we have 1 subtract the square root of a half. So our first answer we have here is x equals 1.707 to 3 decimal places, and our second answer here, x equals 0.2 9, 3 to 3 decimal places. So once again here, we haven't just completed the square, we've completed the square and solved to be able to find our two values for x for this particular quadratic. Our third and final method for solving quadratic equations is using the formula. Now this is a really good method because it works for any quadratic. So all the ones we've used before, the factorisation, the completing the square, all of those examples could have been solved using the formula. Okay? Sometimes you're asked explicitly, solve this by factorisation, solve this by completing the square. However, the formula works for all of the examples we've covered so far. Also, the formula is actually stated on the front of your exam paper on the formula sheet for reference to use during the exam. If you look here on the screen, this is the formula here. X equals minus b plus or minus the square root of b squared subtract 4ac, all divided by 2a. So there's three letters in there, a, b and c, and they relate to the equation that we looked at earlier, the quadratic equation, where a is the number, the coefficient of x squared, b is the coefficient of x, and c is the constant at the end. So these are the numbers you're going to have to look for in the equation to substitute into the formula to be able to solve for x. Let's take a look at an example together. Here we have 3x squared add 4x add 1 equals 0. What's a really good way to start these questions is actually to write down at the side a equals, this case 3, b equals 4, and c equals 1. Your next step is actually to write out the formula. Even though it's at the front of your actual exam paper, rewrite it on the page where the question is. So, x equals minus b plus minus, that's for your two solutions, the square root of b squared, subtract 4ac, 4 multiplied by a multiplied by c, divided by 2a, 2 multiplied by a. Then we have our numbers here, values for a, b and c. We substitute those into the formula. So we have x equals, minus is there, we replace it, stays the same. B is 4, positive, but the negative stays. Add, subtract the square root of b squared. B is 4, 4 squared is 16. Take away, keep the take away. Then we have 4ac, which is actually 4 times a, which is 3 in this case, times by c, which is 1. So 4 times 3 is 12, 12 times 1, just 12. So it's take away 12. All divided by 2a. 2 multiplied by a is 3, so it's 6. 2 times 3 is 6. Then if we simplify this, we can see here, under the square root, we have 16 take away 12, which is 4. So we have the square root of 4. In this case, we don't need a calculator. We know that 4 is a square number, so the square root of 4 is 2. So then we have our two solutions here. We have x equals minus 4, stays the same. Add the square root of 4, which is 2, divided by 6. Then our other solution is x equals minus 4, stays the same. Take away the square root of 4, which is 2, all divided by 6. Minus 4, add 2 is minus 2. So we have minus 2, negative 2, divided by 6, which is negative 1 over 3, if you simplify it. So it's negative a third. Then here we have minus 4, minus 2. Minus 4, go down another 2, is minus 6. Negative 6. Divided by 6 is negative 1. So our two solutions is negative 1 over 3, negative 1/3, and our second solution is negative 1. The next part, the algebra section, is about algebraic fractions. Really, they're normal fractions, but they contain algebraic expressions in the numerator or the denominator, or sometimes both. So for example, if you look here, we have 3x divided by 4x squared. That is an example of an algebraic fraction. Our second example, 2a divided by 3a plus 2. You can see here in this example we have an a here and an a here. These two are examples of algebraic fractions. Now the rules that apply to numerical fractions also apply to algebraic fractions, as we're going to see in a moment when we're simplifying and performing operations. So for example, if we multiply or divide the numerator and the denominator of a fraction by the same number or term, we produce an equivalent fraction, so it doesn't change. So in a similar example that we looked at earlier, if we have the numbers, for example, 3 over 8, and we multiply both by 2, we have 6 over 16, which is exactly the same fraction as 3 over 8. And it's the same when we're dealing with algebra. If we look here, we can see that our original fraction, 3x over 4x squared, has been transformed. So here, all the way along, is exactly the same fraction. So here, from here to here, we've multiplied by 2, here to here, multiplied by y. All the way along, if you do the same to the top and the bottom, the fraction stays the same. So let's look at how this works for simplifying fractions. If we look at the first fraction here, we have 6ab divided by 3ab squared. If we write this out in the long version, we actually have 6 multiplied by a multiplied by b. And on the denominator, we have 3 multiplied by a multiplied by b multiplied by b. And these can be simplified. We can simplify, you can see here that we've simplified the a with the a, they've cancelled. And we simplified the b with the b, and we're just left with one b in the denominator. The numbers can also be simplified. Here we have 6 and we have 3. 6 divided by 3 is actually just 2, so it cancels the 3 here, cancels the 6 here, and we're left with 2. So in the simplest form, we just have 2 divided by b, as you can see here. I'm going to give you 2 minutes for you to try the next two on your own before we go through them together. Off you go. So we look at our second example here. On our numerator, we have 5x plus 2x squared. So the first step, what we can actually do is to factorise our terms on the numerator by taking out the common factor x, which then leaves us with 5, add 2x in the bracket. So the x is the common denominator that has been taken out, the common factor. We then divide that by 3x, as was there before. We then notice that we have an x in both the numerator and the denominator, so we can cancel here and here. This fraction, in its simplest form, is therefore 5 plus 2x, all divided by 3. In this case, we cannot divide the 3 because neither the 5 or the 2 are multiples of 3. So this here is the fraction expressed in its simplest form. If we look at our third example, we can also factorise the numerator. This time there are 2 factors, 3 and b. We take the b out because there is a b in both the first and second term. We take the 3 out because 3 goes into 3 and 12. It's the highest common factor of 3 and 12. So our first term remaining in the bracket is a, and our second term is 4, because we do 3 times 4 to make the 12, and a further b, because our second term here, 12b squared. So we must have b multiplied by b to be able to go back here to the b squared. And that's all divided by ab, which just means a times b. Here, once again, we notice that there is a b on the numerator and the denominator, which can be cancelled. Then we're left in its simplest term, 3 bracket a plus 4b, all divided by a. Once again, this is the simplest term, and we got to there by factorising the numerator to start with. On the next page, you have two further fractions to simplify. Remember to use your rules of factorising to be able to separate out the terms before cancelling. Off you go, you have 2 minutes. If we look at the first one together and look at the numerator, we notice there is an a in both terms. This is our common factor. So a, open bracket, 2 plus a, close bracket. That is the top term, the numerator factorised. If we look at the bottom, there's only an a in one of the terms, therefore it cannot be factorised with a as the common factor. However, 4 and 8, so we can have 4 outside. 4 is the highest common factor of 4 and 8. 2 is also a factor, but it is not the highest. Therefore, we must choose 4. Inside the bracket, we have 2 plus a, close bracket. You'll then notice that our two bracket terms on both the numerator and the denominator are identical, 2 plus a. In this case, we can cancel here and here, which leaves us with simply a over 4. A divided by 4. That is this fraction in its simplest form. Let's look at the next one together. On the numerator, we have 6x plus x squared. X in both terms, therefore that is our common factor. X outside, open brackets, 6 plus x, close brackets. If we look at the denominator, this time we have 3 terms, x squared plus 8x plus 12. This looks similar to the quadratics that we've been looking at in the previous section. So we're going to solve this again by factorisation, but there's going to be 2 brackets. So we need our 2 brackets. The coefficient of x squared is 1. Therefore, it's the simpler method, x and x. So we need 2 numbers to multiply together to give 12, but add together to give 8. So let's look at the factors of 12. We have 1 and 12, 2 and 6, 3 and 4. So therefore, if we are looking for 8, we're going to use these ones, the 2 and the 6. Both positive to make 8, so we have plus 2 here and plus 6 here. We can then write both of those brackets underneath in the denominator. X plus 2, close brackets, x plus 6, close bracket. We've now factorised both the numerator and the denominator. We can then see that we can cancel. X plus 6 is the same as 6 plus x, so we cancel here and we cancel here. Then we have x over x plus 2, and that's this fraction in its simplest form. We're now going to look at adding and subtracting algebraic fractions. Remember, just as simplifying, the same rules that apply to normal numerical fractions apply when dealing with algebraic fractions. The example we have here is 1 over a add 2 over b. Like with normal fractions, we must have a common denominator. To be able to find the common denominator, if we have fractions, for example, 1 over 5 add 2 over 3, we would multiply our first fraction, denominator and numerator, by 3, and we'd multiply our second fraction, numerator and denominator, by 5, the denominator of the other fraction. By doing that, we find the common denominator of 15. So we then have 3 over 15, add 10 over 15, which is simply 13 over 15. We're going to apply the same rules I've just shown you there with the numbers which you know to the algebra. Okay, so we're going to look at this one we have here. First off, we are going to multiply our first fraction by b and our second fraction by a. Remember, it's the top and the bottom, the numerator and the denominator that we multiply by. So we can see here, b, b, we've multiplied. Our second A, which then gives us two new fractions, B over AB, add 2A over AB. These fractions are still equivalent because all we have done is multiply the top and bottom by the same numbers. Here, we're going to multiply it by B, and here we've multiplied by A. We can then add our two numerators together. Like we've done here, 3 add 10, we get our 13. Here we have B add 2A, all over AB. AB stays the same, okay? We don't add our 15 and our 15 to make 30, it's just over 15, because we've got 3 15ths, add another 10 15ths. In this example, we have B over AB, add 2A over AB. So this AB here stays the same. Now you can see here on your page the general rule, which is expressed using A's, B, C and D. It doesn't matter if that sign in the middle there was a takeaway, our final answer would just have a takeaway instead, B subtract 2A. Have a go at the next one on your page, which is P over 3 subtract Q over 2. 2 minutes, off you go. So once again, we need to have a common denominator before we can start adding or subtracting any fractions. Our first fraction needs to be multiplied by 2, both the numerator and the denominator. So I'm going to write in multiplied by 2 just next door to remind myself. 2 because the denominator of the second fraction is 2. Our second fraction we multiplied by 3, numerator and denominator. Why? Because our denominator of the first fraction is 3. It's the opposite way around. If we do that, we're left with 2p over 6. Take away 3q over 6. We can then simply do the subtraction as our denominators are the same. They are both 6. And our final answer is just 2p, take away 3q over 6. We don't know what P and Q are, so we just leave them, the algebra, in the actual answer. You won't be asked to work out the numerical value, but instead expressing your answer using algebra, which has been done here. You now have on the next page 2 examples, one addition and one subtraction of algebraic fractions for you to try on your own. You have 3 minutes, off you go. The first example for adding, we have 3 over x add y over 2. We must multiply our first fraction by 2 and our second fraction by x. That's the denominator that's in the first fraction. It doesn't matter that it's not a number, we can still multiply our terms by x. If we do that, we're left with 6 over 2x add xy, that's x times y, divided by 2x. Our denominators are now the same, 2x, so we simply add them together. So we have 2x. So we add our numerators together, 6 add xy, all over 2x. Again, an algebraic fraction for your final answer. Our second example, we're going to multiply our first fraction by 2q and our second fraction by 4. Write that down, show the examiner exactly what you're doing. If you do that, you then have the following 2 fractions. I've left them in brackets instead of multiplying out. It lets me know here that I'm multiplying everything, that's the 2 add the p, by 2q. Divided by 8q. Again, our second fraction has the same denominator, 8q, and we have 12 as our numerator because we're multiplying our 3 here by 4. If we look at the next step, we then have 2q, bracket 2 plus p, that's the first term, the first numerator from the first term, subtract 12, the numerator of the second fraction. Now here you might want to write this down. Remember to cancel both parts of the numerator, the 2 and the 12, when we're about to divide through now, because we notice that 2 12 and 8 are all multiples of 2 and can be divided. So we are left with q minus 6 divided by 4q. The 2q, the 12 and the 8q have all been divided by 2, so that this fraction is now expressed in its simplest form. Extending what we've just learned, we're going to look at manipulating algebraic fractions by working backwards. So if two terms are added or subtracted in the numerator, like we've just been doing, the fraction can be split in two over a common denominator. For example, 1 plus 2 over 3 can be split into 1/3 plus 2/3. If we were given that, as we had in the last one, we would have gone to this answer here by adding our 2 and our 3 together to give us 3 over 3. But this here enables us to work in the other direction. So we can see here generally, if we have a plus b, two numbers added together, two terms added together, over a common denominator c, we can split those into two separate fractions. However, if the two terms are added or subtracted in the denominator part of the fraction, we cannot split it into two fractions. So you can see here that 3 divided by 1 plus 2 cannot be split into two fractions over 1 and 2. It only works in the numerator. That's an important point to bear in mind as we go through the next part of the section. So a further manipulation that we can do to algebraic fractions is to multiply and divide. And algebraic fractions can be multiplied using exactly the same rules that are used for numerical fractions. So we have a fraction, for example, 3p over 4 multiplied by 2 over 1 minus p. We follow exactly the same rules. So if we had a fraction, 2 over 3, multiplied by 1 over 4, our rules of fractions are simple. When we are multiplying, we multiply our numerators, 2 times 1, 2, and we multiply our denominators, 3 times 4, 12. And that's our answer. So exactly the same thing we're going to do here. P over 4 multiplied by 2 over 1 minus p. So our first step, we're going to multiply them together. I'm going to write that down. If you multiply them together, you're going to be left with 6p in the numerator, and at the bottom, 4 bracket 1 minus p. We can then simplify that because 4 and 6, the highest common factor of those two numbers is 2. So we divide through by 2, we're left with 2 on the bottom, 2 bracket 1 minus p, and on the numerator, 3p. That is the fraction multiplied just like we did with the numbers, expressed in its simplest form. The rule here, you can see the general rule using a's, b's, d's and c's to represent our fraction, we just multiply. So it becomes ac over b, d. So the numerators multiply together, the denominators multiply together. Similarly, when we are dividing fractions, we apply exactly the same rules, whether they have algebra in or not. So if we look at a numerical example to start with, we have 2 over 5 divided by 1 over 4. Our rules for dividing fractions is as follows. Your first fraction stays the same. You then multiply that by the reciprocal of the second fraction. The reciprocal of the fraction is when you flip it. So we have 4 in the numerator and 1 in the denominator. We then follow the same rules that we just looked at for multiplying. 2 times 4, 8, divided by 5 times 1, 5. So the only thing doing we're different when we're dividing is that we actually multiply by the reciprocal. So the first fraction multiplied by the reciprocal of the second fraction. Let's have a look at how that looks when we're dealing with algebra. These are our terms. We write our first fraction out as we have. We multiply by the reciprocal. So that's when we change the fraction round. So our denominator of y subtract 2 actually becomes the numerator and 4 becomes the denominator. So then we multiply across our numerator and our denominator. You'll notice here now that we have 3y minus 6, which can actually be factorised before we move any further. So in this case, our 3 is our factor outside, bracket y minus 2. This helps us in terms of simplifying because you can now see that there is a y minus 2 here and a y minus 2 here. So this and this cancel. You can then see here that across this way we have 2 and 4, which can also be simplified. Divide by 2 and we get 1, divide by 2 and we get 2. We've actually eliminated all of the algebraic terms here. So we have 1 on the numerator and here on the bottom we have 6. So we're left with 1 over 6. So the general rule for dividing fractions is exactly the same as multiplying. We multiply the first fraction by the reciprocal of the second fraction. So it's your turn to have a go now. On the next page you have 4 different calculations. You have 5 minutes to do them and then we'll go through them together. Off you go. So, having a look at these questions now, our first one is matched with our second result here. Our second one matches up here, it was a division one, so make sure that you flipped the reciprocal. You made this one a plus b over 4. Our third one is here, 2 on the top divided by a plus b all squared. And our last one, which is a division, you can see here that we have 2 in the numerator, 5 in the denominator. We make this the reciprocal, so we're actually doing 2 multiplied by 5, which is where your 10 in the denominator comes from here. So what we've gone through together in terms of the operations around fractions with algebraic terms and also the manipulation of the algebraic fractions through simplifying is really important for solving equations that involve algebra. If we look at this question, we have an equation with 2 x's in, and they're expressed as fractions. So we have x divided by 2 add x divided by 3 is equal to 25 divided by 2. So all 3 terms are expressed as fractions, and there's also algebraic terms. So we need to add these fractions to be able to get x on its own, to isolate it to then be able to solve for x. So we can see here that this is similar to adding algebraic fractions. So our first step is therefore necessary to find the common denominator. We find the common denominator by multiplying our first fraction by 3 and our second fraction by 2. We then have our common denominator, which is 6. Our top term we have is 3x, and our second term, which is 2x. We can then simplify our 2 terms on the numerator on the left-hand side. We have 3x add 2x. So altogether, we actually have 5x. 5x over 6 equals 25 over 2. It's then very easy to cross-multiply. We multiply our 2 with our 5x, and we multiply our 6 with our 25, which leaves us with our 10x equaling 150. Therefore, when we solve for x, we divide by 10, we have x equals 15. Once you've actually got your answer, it's always advisable to try and put the answer back into the original question to check whether you've got the right answer. If we've got 15 and we substitute in 15, we have 15 divided by 2, add 15 divided by 3 equals 25 over 2. If we change all these fractions into mixed numbers or decimals, 15 divided by 2 is 7.5, so 7.5. Add 15 divided by 3 is 5, equals 25 divided by 2, that's half of 25, which is 12.5. Is 7.5 plus 5 12.5? Yes, therefore you must have the right value for x here being 15. You now have 2 further examples, which are equations involving algebraic fractions, which I'd like you to solve for x. You have 4 minutes, off you go. Once again, our starting point is to find a common denominator. Our 2 denominators on the left-hand side are x and 2x. So our common denominator is 2x. 2x is like a multiple of x. So if x is your base, as your starting point, you then have 2x, 3x, 4x. Therefore, that's why we can just have 2x as our common denominator. So our first numerator of 3 here is over x. So we must multiply that by 2 to be able to get our common denominator of 2x. So we have 3 over x is the same as 6 over 2x, because we've multiplied the numerator and the denominator by 6. Our second fraction is already over 2x, so it's simply minus 3. 6 minus 3 over 2x is equal to 3/8. At this point we can simplify our left-hand side, so we have 3 over 2x equals 3 over 8. In this situation, it's easy to cross-multiply. 3 multiplied by 8 is 24, equal to 3 multiplied by 2x, which is 6x. We're solving for x, so we divide through by 6, and x equals 4. Once again, we can substitute the 4 back into the equation to check whether you've got the right answer. So here we have 3 over 4, subtract 3 over 2 times 4, 2x, which is 8. To be able to do this subtraction again, it's necessary to change this fraction into 6 over 8. So we have 6/8, subtract 3/8, leaves us with 3/8, which is the correct answer here. So therefore we know that our x being equal to 4 is the correct solution. So in this example, we're going to have to find a common denominator again so that we can add our two fractions. We're going to do this by multiplying, like we did in the other examples, the denominator of the first fraction, x plus 3, by our second fraction, and the denominator of the second fraction multiplied by our first fraction. So if we multiply through our first fraction, we're going to have 5 multiplied by 2x, subtract 1, add 3 multiplied by the numerator of the first fraction, x plus 3. All divided by the first fraction, multiplied by the second numerator here. We're now in a position to multiply out our brackets and to simplify. Make sure you add our equal to on the end here, because we're going to use that to multiply through in a moment. So, by expanding all of our brackets, we have on the top 10x minus 5. Add 3x, add 9. All over these two brackets multiplied together, so x multiplied by 2x is 2x squared. X multiplied by negative 1 is minus 1x, which is just x. Then we have our 3 that we must multiply by both terms in the second bracket. So 3 multiplied by 2x is add 6x. And the last term, 3 multiplied by negative 1 is negative 3. We're now in a position to simplify further. So our numerator, we can collect our x's together and our numbers together. So we have 13x. We have negative 5 add 9, which is 4, all divided by 2x squared plus 5x, take away 3. And that's equal to 2. We can then get these terms here up next to the 2 by multiplying. So 13x plus 4 equals 2, multiply, use a bracket, 2x squared plus 5x, take away 3. Again, we can multiply through on the bracket on the right hand side, 4x squared plus 10x, take away 6. On the right hand side, we have that. On the left, we still have the 13x add 4. Remember, we're trying to solve for x. We need to find out what x is on its own. So we need to now collect our x's together and our numbers together. So this minus 13x here, and subtract the 4 from here. That means we're going to subtract them from the left-hand side and the right-hand side. So here, we still have our 4x squared. We have 10x. We are subtracting our 13x, so we're left with minus 3x. And we're subtracting our 4 from both sides, so here we're left with minus 10. And this thing here, 0. We now have a quadratic expression. We have our 4x squared, take away our 3x, take away our 10. So in this case, what we can now do is actually solve for x. So again, we went through the 3 examples earlier of factorisation, completing the square, and the formula. So we can use whichever method you feel is most suitable. As I mentioned before, the formula can be used in all cases. So if we were to use the formula, we would have a equals 4, b equals minus 3, and c equals minus 10. In this case, our formula being x equals minus b plus minus the square root of b squared minus 4ac, all divided by 2a. If we substitute in our values here then, we have negative 3, we'll deal with that in a moment, plus minus the square root of minus 3 squared. Then we have take away 4 times 4, that's a, times minus 10. All divided by 2a, which is 8. So we then have negative 3, which is positive 3, plus or minus. If we look here, we have 9. Here we have 4 times 4, which is 16, multiplied by negative 10, which is negative 160, and we're actually adding them. So here we have our 9 add our 160, because there's 2 negatives together, which is actually 169. The square root of 169 is 13. 13 times 13 is 169. All divided by 8. So for our 2 solutions, we have 3 add 13 divided by 8, and 3 subtract 13 divided by 8. 3 plus 13 is 16 divided by 8, which is 2. And on here we have 3 subtract 13, which is negative 10 divided by 8. So 8 into 10 goes once, remainder 2. That's 2/8, which is 1/4, which is 0.25. And remember to include the negative. So here we have our 2 solutions now. X equals 2, x equals minus 1.25. If we go back to our original question, we have here an equation with x in. We can substitute our value for 2, which is our positive value, to see if we come through to the right answer. So we have 5 over 2 plus 3, which is 5. Add 3 over 2 times 2, which is 4. Take away 1, which is 3. So we have 5 over 5, 1, plus 3 over 3, 1, equals 2. Perfect. So when x equals 2, we've got the right answer. So here we know immediately that the solution to our equation here with x in is that x is equal to 2. X will not be the negative solution down here as we've seen our other solution, because in this example x can only be one value, and as we've seen here, the 2 substituted through make sure that this equation of our 5 over x plus 3 add our 3 over 2x minus 1 is actually equal to 2. So here, x equals 2. Once again, from the top, to solve this kind of problem, you need to make sure that you find a common denominator by multiplying your second fraction by the first denominator, and multiplying your second fraction by the first denominator, multiplying all of it out. In this particular example, we were then left with a quadratic, which then needed to be solved by factorisation to be able to find the solution for x. So we've now reached the end of the third section on algebra. You're going to pause the video and take a 10-minute assessment on the two key algebraic skills we've been practicing, solving quadratic equations and quadratic fractions. Good luck. The fourth section of our DVD is on shape, which consists of two topics. Our first one is vectors, and our second is triangles. We're going to be using vectors to solve problems, and in the triangle section, we're going to be looking at the sine and cosine rule, and a further rule around finding the area of a triangle. A vector is a quantity that has both size and direction. Size is sometimes called magnitude, and a vector can be represented using a line segment with an arrow on it. You can see here we have a line starting at A, travelling to B. The direction, which is here one of the key aspects of a vector, is from A to B. That's why there's a little arrow here on the line. And then there's an A, a value for it, and that represents the size of this vector. The vector can be written in many ways. The most common way you'll see in your exam paper is a capital A and a capital B, which is A to B, A first to B. And to make that clear that it's a vector, there's then a little arrow above. Another way is just writing it A, that's the value across, and sometimes you'll see it A with a swiggle underneath. You can also write this or express it numerically. You can see from A here to B, we can travel along here, the horizontal, and to travel along here, we travel 1, 2, 3, 4, 5, 6 units. And to get from here to B, we travel up 3 units. And we can express this as a column vector. A column vector is used also for translations. Here, the number at the top represents the horizontal movement. If you're going in a positive direction, that's moving right, think about an axis on a graph, and moving this direction is the positive. As we're doing here, from A across, we move 6. And that means our first number is 6. If we were moving left, just like we would when we were expressing a column vector for translations, it would be a negative number. And from here, we're going up. Upwards is also a positive movement. If you are here on the axis and you're going up, the number's becoming more positive. So here we have 3. So these are the different ways that you can express this vector. So a vector is a line that has both size and direction. This one has a size across 6 and up 3, and it's going in the direction of A to B. As I said, this is the most common notation used, AB with an arrow over the top. In our example here, we also go from A to B. This time, however, we travel 5 across and 2 up. So the column vector changes, 5 on the top, 2 on the bottom. Now, suppose the arrow went in the opposite direction. It started at B and went to A. We called the vector A to B, A. If we're going in the opposite direction, it's actually the negative, and that's why here you have negative A. We can also describe this vector as B to A, this one here. So we're starting at B, B is the first letter to A. As I've already said, you describe it with a negative A, going backwards, or actually if you're starting here at B, instead of moving 5 right, you'll be moving 5 left. So the number at the top here changes to a negative. Similarly, when you get to this point, to get to A, you'll be moving down, go down 2. Therefore, this number here, instead of 2, is actually negative 2. Vectors can also be multiplied by scalars. Scalars have size but no direction. So a scalar quantity can be represented by a single number. If we look at our first vector here, which is A, if we multiply that by 2, the scalar 2, our new vector becomes 2A. We can see this as well if we look at the column vector. From this point, we go across 3 and up 2. So our column vector is 3, 2. if we've multiplied our vector by the scalar 2, we would expect our new vector to be 6, 4. Let's check. We start here, 1, 2, 3, 4, 5, 6 across, 1, 2, 3, 4, 4 up. So yes, our vector which started as A has now become 2A. So on our last 3 slides, we've seen 3 important points around vectors. Firstly, the notation, how they're actually written. The second point around the negative when they're going in the opposite direction. And the third point here now around multiplying by scalars. We're now going to look at adding and subtracting vectors. Adding 2 vectors is the equivalent to applying one vector followed by another. If we look at this example, we have vector A, which is expressed as 5, 3. 5 to the right, 3 up. B is expressed as 3, 3 to the right, 2 down. Remember, the direction of us tells us where we're starting. So this one here, we start here, 3 across, positive 3, 2 down. We can either travel up A and down B. Or actually, what might be quicker, starting here, we can go straight from our start point to our end point, which is the equivalent of going through A and through B. That's applying one vector, A, followed by B. If we look at this line, we're starting here, we're going across 8, that's 8 right, and we're going up 1. So actually the vector AB is 8, 1. Look back at the original, where A is and where B is. Well, A is 5 here, 3 here. 5 plus 3 gives us our 8 here. 3 add negative 2, which is 3, take away 2, is 1. So that's here. So it's perfectly acceptable to add vectors, and instead of going up here and along, we can go straight from here to here, which is just A plus B. So the vector notation of travelling from here to here is A plus B. Subtraction is very similar. We're going to have a look at this subtraction here of A take away B. To show this subtraction in a diagram, we can think of A take away B as A adds, that's the followed, by the negative of B. So from here, we would travel from here through A, adding the negative of B. The negative of B, because this here, this vector, B, is going in this direction, and we need to go in the other direction. So this is why here we have our negative. So our B vector is negative 2 and 3. We're going to be going in the opposite direction. 2 right, positive, 3 down, negative. So we have 4 and 4 for our first vector A, and then we're actually going negative B, not B. So it's 2, positive, negative 3. And that's where our 6, 1 comes from. We add these together and we get 6, 1. And that's our vector of A take away B in this direction. Now, in the actual problems you're going to come across in your exam, you're not going to need to use the column vectors. You're only going to have to use the notation. So what's really important is the positives and negatives depending on what direction that you're going on, and you'll see in a moment. So vectors can be used to solve many problems involving physical quantities such as force and velocity, and can be also used to prove geometric results, such as this one below. For example, suppose we have a triangle ABC. We have a diagram here, ABC triangle. The information we're given is as follows. The line PQ, that's here, is the midpoint of the line AB, so it's halfway along AB, and Q down here is also the midpoint, but of A and C, halfway. Your task is to show, using vectors, that PQ, this line, is parallel to BC, and that the length of BC is double the length of PQ. I'm going to use vectors to do this. So I'm going to give you 2 minutes to think about it, and then we're going to work through the problem together. 2 minutes, off you go. So this question, like many proof questions, involves you needing to actually set notation. So the first step is to define the vectors. Let's look from A to P, our first line segment. We're going to call that vector A to P. The second step is to define the vector A to Q, and that simply could be B. You can choose any letters for these as long as you're consistent. So A for this one and B for this one. As soon as we've got that, we immediately can spot the vector PQ. The vector PQ, starting at P here, we're going to go backwards on A and forwards on B. So with our notation there, we have backwards on A, forwards on B. Negative A, B. And it's more mathematically correct to have the negative there at the end. So the vector PQ is expressed as B subtract A. Our next step is to look at the vector BC, the parallel line which is double the length. So looking at this one, our first step is to see here. We want to go from B to C. We know that P is the midpoint. If we know the vector from A to P is A, the vector from A to B must be 2A. It's double the length. If we then look at our vector from A to C, we know A to Q is B, and it's double. Q is the midpoint. So A to C is 2B. And we want here B to C. So we're going to go backwards on our 2A, forwards on our 2B. So we have minus 2A, add 2B. Again, writing that round the way that we have our positive first and our negative here, gives us 2B subtract 2A. We can then factorise here by taking our 2 outside the bracket, 2 bracket B minus A. Now if we compare these two lines now, we have for our vector, first vector, PQ, is B minus A, and our second vector is double the amount. That's what the 2 here in front of the bracket denotes. Therefore, BC, the vector at the end, is equal to 2 lots, that's the 2 here, multiplied by the vector PQ. So we can see here that both of our vectors for PQ and PC are parallel because they contain the same element, B minus A. However, the only difference is that BC is double the length. That's where the 2 is in front. Make sure when you're answering any proof questions that you also write a sentence here, like I've done, to explain the actual proof as well as the mathematical working out. The next question has 2 parts. First off, you need to write the following vectors in terms of A and B, and then we'll look at some midpoint questions. You have 3 minutes to complete the first part before we go through it together. Off you go. In vectors questions, it's often handy to have an extra pen with you to be able to draw on lines and show where the vectors actually are. So if we look at our first one, we'll ask for the vector BC. So the vector BC is here to here. Now to get to BC, we're just simply going to do the same as we do down here, so O and A. This shape is a parallelogram. So this length here is equal to this length. It's equal and it's parallel. Therefore, it's the same vector. So that vector is just A. Our next one is CA. From our corner here down to A. Now the opposite side of the parallelogram over here, OB, also has a vector expressed, but it's B here. However, it's going in the opposite direction. It's going from O up to B. You want to be going from C down to A. So this is where we're going to apply the negative. So the vector C to A is actually negative B. You're expressing that vector using the A and B terms, which in this case is negative B. Our next one is actually travelling across the parallelogram. We need to go from A, we start here, and we're going across to B. So if we're starting here and we're going across to B, we're going backwards on A, that's negative A, and forwards on C. So we have negative A, that's backwards, and then up, plus B. Like we saw in the last example, it's better to write that as B take away A. The fourth one here we're asked to find is O to C. I'll do that in purple going across here. We start at O and we go to C. So we're travelling up, B is positive, and then across. Now we worked this vector out as the first one we worked out, B to C, which was A. So here we're travelling B plus A. And these questions are very typical. Often you're asked at least 2 or 3 of these at the start of a vector question. Then it may go on to add further information. In this case it says X is the midpoint of OA. Let's draw that in. So OA is here, X is the midpoint, it's halfway. Y is the midpoint of OB. So halfway here, we're going to have Y. We're also asked to find the vectors in terms of A and B again. So all of our answers are going to have A's or B's in and numbers, that's all. So our first one is OX. So we start here and we go from O to X. Now that's halfway O to A. So we know the vector O to A because it's given as A. So if we're going half the distance, it's simply half A. The next one we're asked to find is OY. Similarly, from here, we're going halfway up B. The normal vector from O to B was B, so halfway is just half B. And the last point we're trying to find out is the vector from actually the 2 midpoints, X and Y. So I pop that in purple here. The direction is important. X is first, Y is second. So we're starting at X and we're going towards Y. I'm drawing an arrow on there. So we're going backwards on the half A and forwards on the positive half B. So in this case, we have minus a half A. That was the vector X to O. Add the vector O to B, which is a half B. Again, if you want to write that with the positive first, half B, take away a half A. And that's expressed using the terms A and B. In the next question, you're giving a triangle, OTP. And it states that M is the midpoint of O and P. Again, it's labelled on here. You're also given 2 vectors, OT, which is A, and TB, which is B. And you're asked to write the following vectors in terms of A and B. There's 2 vectors. I'm going to give you 3 minutes and then we'll go through it together. Off you go. So the first vector we're asked to find is from O to M. We know that M is the midpoint of OP. If it's the midpoint, it's going to be half the value of OP. So our first step is to find the vector OP. Starting at O, going to P. We start this way, we go along A, that's positive, and then we go from T to P, which is up in this direction, which is positive B. So the vector OP is equal to A add B. But we're asked to find the vector OM, which is half. So OM, which is equal to half OP. So it's this vector halved. So we put half bracket A plus B, which tells us it's half the whole vector of OP, which is A and B. The second vector we're asked to find is TM, this one. We look at T here, and we want to travel to M. Again, I'm going to draw the line on, little arrow with the direction I'm going on. I'm starting at T and I want to get to M. There's two ways I could do this. I could go up to P and then down to M, or I could go across to O and up to M. Either way will be fine. Let's do both. So our first one, if we're going up to P, we're going to add the B, and we're going to go backwards on the vector OP. This time we're going PO. So it's going to be the negative. But we're only going halfway. So we're doing the negative half of OP. So in this case, we're going to have this OM, which is all the halfway, which is the same here, but we're going to have the negative. So we have a negative, a half A, and a negative half B. This is the first time now that we can actually simplify a vector we've seen. So we have two terms which contain B. So we have B, take away a half B. That leaves us with just a half B. So we have a half B, take away a half A. Again, you can factor out the half, so you can put a half outside the bracket, B, take away A. Now that was going this way, up B and down here. So just to prove it doesn't matter which way you go, we're also going to do it in the other direction to get this answer here. So if we're going in this direction, we go backwards on A, so that's take away A, and then we're going forwards on the OM. And we've already worked out the OM, which is a half. So we're going to add a half A plus a half B. Simplify now, we have two terms that contain A. We've got minus A, add a half A, is going to be take away a half A. Add a half B, and we have our terms here. Again, it's easy if we have our positive term at the beginning. So here we have a half B, take away a half A. Once again, remove your half outside the bracket, and we're left with B, take away A, which, as you can see, is the same answer that we have here as we have here. So once again, it doesn't matter if you're going from the vector T to M, whether you go this way, which is the yellow route, or you go the green route. You're going to have come here to the same point. You're starting at T and you're ending at M. So another question for you to try. ABC is a triangle. AC, that's the vector, A to C, equals X. The vector AB, as you can see on the diagram here, AB is equal to Y. CT, which is a point just here, CT to the ratio TB is 1 to 2. So this section here, T to B, is twice as big, we don't know how big, but twice as big as the section C to T. So if C to T is 5, then T to B is going to be 10. It's going to be double the amount, okay? So here we're given a ratio to help. We want to write the following vectors in terms of X and Y this time. They've changed the letters A to B, the same process is applied. So the first vector you need to find is BC, and the second vector is AT. I'm going to give you 3 minutes to have a go on your own, then we'll go through it together. Off you go. So our first question, we're asked to find the vector B to C. So if I take my highlighter, so this is the vector we're finding, and importantly, this is the direction. So I'm starting at B. I'm going backwards on the Y, so that's a negative, and I'm going forwards on the X, that's a positive. So this vector is positive X, take away Y. Negative Y, positive X, adding. The second vector you're asked to find requires you to use the ratio given in the question. The vector you're asked to find is the vector A to T. Once again, your first step is to actually draw this vector onto your diagram. And it's the green one that I've just drawn. It starts from A and goes to T. Important to draw the direction on. We can see here we are starting at A. So we're going to go through X, positive. And then we're going to go backwards on this line here. We know that B to C is equal to X minus Y. So in the opposite direction, that's C to B, it's going to be Y take away X. Exactly the same, but the negative of it. Negative, positive Y, negative X. But we're not going the whole way. Remember, this vector we're asked to find is AT. We're only going up to this value here. Now, we were told that this section is worth 1 and this section is worth 2. So we're in the ratio 1 to 2. And the best way to think about this is in parts. So really, the whole section from C to B is 3 parts. And we only want 1 part of it. So whatever the vector is from C to B, which we've just worked out, we only want 1/3 of it. 1 out of the 3 parts. So we simply put 1/3 bracket the vector Y take away X. That there just gives us a portion of it. If we wanted the section from T to B, that would be 2/3, 2 out of the 3 parts. So we add this part, that's the C to T, to our first part, A to C. So we have X, add our new vector here. So X, add 1/3, bracket Y plus X. Again, if you multiply out your bracket, you'll then have a term with X in, which you can simplify with the other X. So you have X plus 1/3 Y, take away 1/3 X. The Y, there's only one Y value, so that stays the same. That's 1/3 Y. We have a whole X, and we're subtracting 1/3 X. So we're left with 2/3 X. So our vector, AT, is 1/3 Y, add 2/3 X. For the next question, we're giving the following information. The vector OA is 4A. The vector OB is 4B. OAC, OBX, and BQC are all straight lines. We can see this information clearly from the diagram. It's just clarifying that they are actually straight lines. You might want at this stage to write in your vector OA, which is here, which is 4A, and put the direction on as well. Remember, that's really important. O to B, this one line here, is 4B. We're then given some further information to consider. AC is equal to 2 lots, that's the 2 in front of OA. So if we know that OA is 4A and that AC is equal to 2 of those, we must multiply our 4A by 2 to get 8A. So this section here from A to C is 8A because it's double. AC is equal to 2 lots of OA. Some further information we're given is about BQ and QC, that they're in the ratio 1 to 3. Now we don't know any information about the lengths or the vectors of BC or CD at the moment, so that information we'll have to use in a moment. We're first asked to write the following vectors in terms of A and B. And our first vector we're asked to find is BC. So with the highlighter, I can go here from B to C with the arrow. So I'm starting at B. That means I'm going to go backwards on the 4B. So it's a negative 4B. And then I'm going to go forward on the A's here. But I'm going from O to A and then from A to C. So altogether, I'm travelling positive 12A. Again, if you want to rearrange that, It's 12a take away 4b. That's the expression for the vector from B to C. The next one we're asked to work out is from A to Q. If I mark that in green here, it goes from A to Q. Again, the direction is important. We start at A and we go to Q. Now we're given some information here about the ratio of this length. We've just worked out BC, the whole length up here, and it's divided into 4 parts. So this section from O to Q is only one part, one of the 4 parts. So it's actually a quarter of the whole part. So we know here the whole part, so we can then work out that B to Q is just a quarter of that. Well, a quarter of 12a is just 12a divided by 4, which is 3a. And the second part of minus 4b, a quarter of minus 4b, is just 1b, and it's a negative, because we started here with negative 4b, so it's minus b. That's a quarter of the way. So from P to Q here, it's a quarter of the whole distance. So if we're starting from A and we want to get to Q, we need to go backwards on our 4A, so that's negative 4A, forwards on our 4B, so that's plus 4B, and we need to go forward on our section here from P to Q, which we have here as 3A take away B. As in our previous example, there's no reason why, when we want to travel from A to Q, that we can't go in the other direction. We will get the same answer. So simplifying our terms now, we have 4b subtract 1b, leaving us with 3b. We have minus 4a add 3a, which leaves us with minus a. So our vector here from A to Q is actually 3b take away a. The next section we're going to look at together is the sine and cosine rule. This is an extension of trigonometry. You would have met at B grade SOHCAHTOA. SOHCAHTOA is used when solving problems involving right-angled triangles. Sine and cosine rules can be applied when we are given non-right-angled triangles. If you look here at this triangle on the screen, it's really important the labelling of the triangle as your first step. You can see that all of the vertices, the corners of the triangle, are labelled with capitals A, B and C. The sides opposite them, for example, C is here, the side opposite is labelled as lowercase c, and that's the same for B and A. It's really important you stay with these conventions. If you were given a triangle which is labelled differently, for example P, Q and R, I would advise you to re-letter the corners, vertices and the sides as A, B and C, and make sure that your corresponding sides link up. For example, if this is A, your side over here will be labelled with a lowercase a. This convention is going to help you when you apply the rules. On the screen now is a slide of really important information. First off, on the right hand side is a guide as to which rule is used when. You can see that a sine rule is used when a question involves 2 angles and 1 side. It can also be used in situations where there are 2 sides and a non-included angle. A non-included angle, for example, if you are given this side, which is 10, and you are given this side, which is 6, the included angle is this one, because it's between the 2 sides, 10 and 6. A non-included angle will be the blue one here or here. So a sine rule is used in the situation where you have 2 sides, for example 10 and 6, and a non-included angle, which are the 2 blue ones labelled here. The cosine rule is used in situations where you have 2 sides and the included angle. That was the first situation I described. That was this side, and the included angle, the angle between the two sides. The other situation the cosine rule can be used is when you have three sides and no angle given. If we look now down here to the rules, the two rules that are given on your formula sheet are the first ones here and here. This is the sine rule for finding sides and the cosine rule for finding sides. However, you can easily change or remember how to change the formula to be able to find angles. You can see here that it's very similar to our first rule, but it's the reciprocal. So all of our signs are on the top and our letters here, A, B and C, are on the bottom to represent the sides. You can see here that the cosine rule given in the formula sheet has been rearranged so that cos x is on its own. If we add our term at the end here, 2bc cos a, to the right-hand side and subtract our a, we're given 2bc cos a. So we are adding it and we're subtracting our a squared. We then have b squared plus c squared, take away a squared. To be able to find cos a, we need to divide all of that by 2bc. And that comes down here. So this is the rearrangement here that's necessary to be able to find the angle. And that's the angle A that you're missing. So they are on the formula sheet. You can use them, but you do need to know how to rearrange them and also how to apply them. So we're going to be doing that in a series of questions together now. So we're provided with the following information. AB is 5 centimetres. AC is 12 centimetres. Angle ACB is 21. ACB is 21 degrees. And our other angle, BAC, is 43. And we're asked to find the length BC. BC. This is our unknown. And we're asked to give our answer correct to 3 significant figures. In this case, we're going to be applying the sine rule. We have 2 angles and 2 sides. We're only going to be able to use one of the sides. If we look here at the sine rule, we have A over sine A equals B over sine B, which is equal to C over sine C. Remember, it's at the front of your booklet. Copy it down where the question is. You will notice that we will only ever use 2 parts of the sine rule out of the 3. In this case here, we're given C, the length, across here being 5, the angle being 21. That's a pair we have. We're trying to find the x, and we know the corresponding angle, which is A, is 43. So in this case, we're going to use this and this, and we know they're equal to each other. It doesn't matter about this B here in the middle. If we write this out again, we have A divided by sine A equal to C over sine C. And then we simply substitute in our values. So we have A is our unknown here, so we can put x in, divided by sine A, which is sine of the angle 43. That's the angle on A. Is equal to C, the length here, AB, which is 5, divided by sine 21. So here we now need to find the x on its own. So we rearrange. Here we have x divided by sine 43, so we simply multiply this here by sine 43. So we have x equals 5 divided by sine 21, all multiplied by sine 43. We then type that into our calculator, making sure we do the first part separately. So 5 divided by sine, button on your calculator, 21, close my brackets, multiplied by sine 43. We're going to get a decimal out. We're going to write all the numbers down. It's good practice. 9.5153 33697.3. Recheck the question. It says give your answer correct to 3 significant figures. So go back and then round 1, 2, 3. So it's going to be 9.52. The 1 rounds up. So it's going to be 9.52 centimetres. In the context of this question, where the other sides were 5 and 12, 9.52 seems a reasonable answer, which you can be happy with and move on to the next question. On the next page is a question for you to try. Again, we have a triangle, and you're asked to find the length A. I'm going to give you 3 minutes applying the sine rule to find the unknown side. Off you go. Before we start working out, let's look at the triangle. We have a corresponding side and length, 39 and 7. That's for the B part. We then have our angle here of 118 and our missing side that we're trying to find, which correspond, and that's the A part. So when we write down our sine rule, we're going to be using A over sine A equals B over sine B. Again, we're finding the length. We have 2 angles and a side. That's why we've chosen the sine rule. If we substitute in our values again, we have A, our unknown, divided by sine 118 equals to 7, the length here, AC, divided by sine 39. Substitute that all into your calculator, rearrange, and the answer you get for A is 9.82 centimetres, correct 2 decimal places. Again, in the context of the question, with our other side being 7, 9.82 is a reasonable answer to expect. We're now going to look at the sine rule, but instead of finding lengths, we're going to use it to find angles. If we look here at our triangle, we're given 2 sides and an angle, but it's a non-included angle. It's not between our 2 sides we're given 8 and 6. Therefore, we're using the sine rule. However, the formula we're given at the beginning of our booklet will have to be rearranged so it's appropriate for finding angles, which can be done as follows. We have our sine B on the top this time in the numerator divided by the length B. And similarly here for the A, sine A over A. We see here that our A side, 6, and our 46 correspond. And then we'll be able to find our missing angle here, B, which corresponds to our 8 centimetres. We substitute in our values to get sine B over 8 is equal to sine 46 over 6. Rearranging this will give us the value for sine B. Sine B equals 8 sine 46, all divided by 6. Now here, to find the missing angle, we're going to use our inverse function. You may need to use the second function button. It's exactly the same for trigonometry when you're finding angles on your calculator. So our value for our angle is going to be sine to the minus 1. That's the inverse sine. And then the same fraction we had before, 8 sine 46, all divided by 6. And the answer is 73.56 degrees, correct to 2 decimal places. Once again, in the context of this question, an angle of 73 is an appropriate size for the angle. You will notice you already have the angle of 46. Adding your 73, it still is less than 180, leaving room for your final angle here at C, which you could calculate by adding your 2 angles up and subtracting them from 180. So the next question is for you to try on your own first. You're asked to find the angle A. You have a triangle ABC. You're given 2 lengths, 10 and 7, and a non-included angle of 61. You have 3 minutes, off you go. So once again, we're using the formula for angles. So we have the sine rule with our sine B at the top, okay, divided by our length B equal to sine A divided by A. Again, we have here pairing on the B side and then here on the A. And we're trying to find our missing angle here for A. So our first step is to substitute our values into the formula we have. Sine 61 divided by 10, that's your part for B, is equal to sine A, our missing angle, divided by the length, which is 7. We rearrange that to find sine A. We do the inverse to actually find the angle. So then to use your calculator to work this out, it's much easier if you place brackets here around your term. Then using your calculator, you're going to do the inverse, the sine, and then you're going to be doing 7 sine 61, all divided by 10, which gives us a value of 37.8 to 3 significant figures. And this here is a value for the missing angle here at A. Once again, in the context of this question, 37.8 is an appropriate value for an angle, which would be missing in this particular triangle. We're now going to move on to some practice using the cosine rule. Our first example is to find a length. You will notice you are given two lengths, 6 and 5, and an enclosed angle of 50. I'm going to give you 1 minute to think about the cosine rule and how you might substitute your values into it to solve this particular problem. Off you go. As we discussed earlier, the cosine rule is also given on your exam booklet. The format it's given in is that enables you to find the lengths, which you're asked to do in this question. So you need to rewrite as your first step the cosine rule on your sheet at the particular question. So we have a squared equals b squared, add c squared, take away 2bc cos a. We then need to substitute in our value. Now you'll notice this triangle is not labelled, and as I said earlier, sometimes it's labelled and sometimes it's labelled with different letters. The really important thing, especially when you're doing the cosine rule, is that the angle that's given here is labelled the A part. So we have A here, and the others it doesn't matter, but we can have B and C. There are two other sides that we're going to square in a moment. If we substitute in our values here, we then are given A squared equals 6 squared plus 5 squared. They're the other two sides. Subtract 2, the 2 is constant, the two sides, 6 and 5, multiplied by cos 50. Cos 50 is the angle here. And then you can work out individual sections if you'd like to ensure you've got the right answer. So we have our 6 squared plus our 5 squared, and we know that there equals 61. So our first step for this part will be 61. We then need to take away our second section, which is 2 multiplied by 6 multiplied by 5 multiplied by cos 50. It's really important that you're doing this at the same time and actually put it into your calculator to ensure that you're getting exactly the right answers out as well. So here we have 38.56725658. So we're going to round that to 3 significant figures. So we're going to take away 36.6. Now that's going to give us a squared. We don't want a squared because a squared is not going to give us the length. It's going to give us the area on that length. So we must do 61, take away our answer from before, and then square root. So 61, subtract our previous answer, and then square root that answer. So once we have this, we will then square root, and we'll come out as 4.74 centimetres, correct to 3 significant figures. Again, in the context of this question, 4.75, yeah, the other sides are 6 and 5. We can't measure them, the diagrams are not drawn to scale, but it's a reasonable length given the other information in the question. So the next question is for you to do on your own. You're asked to find the length of the side A. You're given the length 4 and 7 and the angle 48. 3 minutes, off you go. So once again, in this question, your first step is always to write the rule out that's given to you in the formula booklet, which is given there on the screen. We then substitute in the values in this particular question. and write it out. If you only put it into your calculator and then make a mistake, you're not going to be able to get those marks for working. Really important. If you pop that into your calculator, you then come out with the answer 27.53. Now, often people stop at this point, but 27.53 is actually equal to a squared, not a. Also, 27.53 is much bigger than the other sides. So if you're doing that test, is my answer reasonable? At this stage, you'd say no. And then you'd realise that this is actually equal to a squared. So you must square root 27.53 and you get the answer 5.25. This again is correct to 2 decimal places. 5.25 is a much more reasonable answer given our other two lengths are 7 and 4. Again, it's really important to make sure you're rounding to the correct number of decimal places or significant figures, and that's by rereading the question to check that you've done your answer to the correct degree of accuracy. As you've seen already with the sine rule can be used to find lengths and angles. The cosine rule can also be rearranged as we looked at the beginning of this section so that you can use it to find angles. Here we're given 3 sides, but no angles, and asked to find the angle at B. If we mark the angle on, this is the angle here that we're looking for. The formula that we're going to be using is as follows. Cos A equals B squared plus C squared, take away A squared, all divided by 2BC. Now if you look at your triangle, the angle that we just labelled around the B is the one we're looking for. So this here is the B part. So this is the angle that we need our cos to be associated with. And it's often easier, instead of changing your letters in the formula, to actually change your diagram. Therefore, your formula stays exactly the same every time, and all you're doing is changing the letters on your diagram. So I need this side here to be the A. So I'm going to write over B to make it A. And then the other two, it doesn't matter, you need to change them. B, and that one can still stay as C. So that's an important step because your cos A, the angle you're trying to find, needs to be related to this angle here. So if we then substitute in our values, we have our other two sides, the B and C side, squared. That's 12 squared and 10 squared. And we're taking away the A squared. Really important there that I've rearranged this so that this is 6 squared. Dividing by 2BC, 2 times 12 times 10. Substitute that into your calculator. Again, with these kind of questions, sometimes it's easier to actually work the top out and then the bottom separately. So on your calculator, with me at the same time, we're going to have 12 squared, add 10 squared, take away 6 squared, again 206. And then we're going to be dividing our 206 by 2 times 12 times 10. 2 times 12 is 24, multiplied by 10 is 240. That's for cos A. I don't want cos A, we need A. So what we're actually going to have to do here, just like we use in the sine, we're going to be using the inverse function. So we're going to be using cos to the minus 1, bracket 206, our first value, divided by 240. So on your calculator, with me at the same time, find your cos to the negative 1. It's often the button you must press shift or second function to get to. Open your bracket, 206 divided by 240. And it comes out 30.87003845. Again, we're going to be asked to round this, normally to 3 significant figures. So rounded is 30.9. In the context of this question, does 30.9 seem reasonable? Well, yes, we've got 3 angles in a triangle. They all need to add up to 180. So 30.9 is a reasonable size for an angle. So lastly, now it's your turn to have a go at finding an angle using the cosine rule. You're given a triangle. It has 3 sides of 8, 6 and 4, and you need to find the angle missing, which on this particular example is A. You have 3 minutes, off you go. So again, your first step is to rewrite the formula that is at the front of your booklet. Rewriting the formula for cos A, that's to be able to find the angle A. Remember last time we had to relabel the triangle to ensure that the angle part was the A. And here we're asked to find A. So already we're looking for this angle, which is A, and our corresponding side is H. So no need to rearrange the letters associated with the triangle. If we substitute in our values then, we have cos A equals 4 squared plus 6 squared, they're the two sides. Subtract the side opposite the angle we're trying to find, that's the 8 squared. All divided by 2 multiplied by 4 multiplied by 6. If you work that out, you're left with cos A equaling negative 0.25. Again, you must use your calculator and the second function button, that's the cos to the minus 1. The cos to the minus 1 of negative 0.25, as you can see here on the screen, is going to give you an answer of 104.48. That's correct at 2 decimal places. Is that reasonable? Well, it's an angle, and if you look at the diagram, even though it's not accurate, you can see that this angle is obtuse. It's larger than 90 degrees. So an angle of 104 is larger than 90 degrees, but not too large that there's still room for the other two angles so that all three angles add up to 180 degrees. Now we practice using both the sine and cosine rule for finding lengths and angles. We're going to apply these rules to finding problems. Again, I mentioned at the beginning of this DVD that there would be functional style questions included. The following questions are of this sort. Our first problem is about an aeroplane that starts at the airport A. It flies 8.5 kilometres on a bearing of 060, a 60 degrees angle, but bearings are expressed with 3 figures. It then gets blown off course on a bearing of 160 degrees for 7 kilometres, after which the captain decides to fly home. Your task is to find how far you have to fly and in what direction. You have 5 minutes to tackle this problem before we go through it together. Press pause and have a go. As with many of these problem-solving questions, they require several steps, so it's best to go one step at a time and break the question down. So the first step that you need to be able to do is to find the angle between 8.5 and 7. So we have 8.5 here and 7 here. These are our two lengths. So the angle I'm referring to is just here. The way we're going to use this is just by using angle facts. We have an angle here of 60 and we have the angle here. These angles here are called supplementary. They're like a C shape upside down. And these supplementary angles add up to 180 degrees. So our missing angle on this side must be 120. We then know that angles at a point add up to 360 degrees. So if the two other angles, 160 and 120, add up to 280, and they all three add up to 360, our missing angle just here will be 80. Our second step is now to apply cosine rule. The reason why we're applying cosine rule is because we have two sides and an included angle. The sides, 8.5 and 7, and our included angle is 80. If you apply the cosine rule, you're then going to be able to find the distance on the opposite side, which is here where the plane is, which comes out as 10.0, 3 kilometres, correct to 3 significant figures. The final step is to be able to use the sine rule to be able to find the angle between 7, the length here, and the home direction here. So the angle that we're trying to find in purple is this angle here. So we have our length here, which is 10.0. 3, we have our length here, which is 7. We have our angle of 80. We have our length here of 8.5. So we have a pair of corresponding sides here, the 80 and the 10. And then we have our missing part. Here we have 8.5, and we're trying to find our angle here. So we're actually going to use the angle, which is the sine A, over A being equaling to sine B over B. We've got our lengths here, which are 10.0, 3. And we have our length of B here, which is 8.5. We have our angle of 80. And then on this side, we don't know the angle. That's the angle we're trying to find. If you substitute these values into your calculator, then you can then find the missing angle here in purple, which is 56.6. Is that a reasonable size for an angle? Yes. The other angle is 80 plus your 56.6, and there's still the remaining angle here, so they add up to 180. So you can see there that you've applied angle rules, you've used the cosine rule and the sine rule just to be able to find here our missing length of 10.0. 3. A complex problem but worth lots of marks in the exam, so persevere, get to the end. So I have one further problem for you to try. This question is about a surveyor who is trying to calculate the height of a tower. He measures the angle of elevation at 32 degrees. He then moves closer by 15 metres and the angle is now larger. It's now 42 degrees. And your job is to find out the height of the tower. Now this information has been represented in the diagram below. You can see here that the surveyor is originally standing at this point where he measures the angle of elevation of 32. He then moves in 15 metres to measure the angle here, which is then 42. And you need to find the height, which is there. I'm going to give you 4 minutes to think about this before we go through the question together. Press pause and have a go. A good tip when you're doing these questions is before you actually start on the work, think about anything that you've spotted or you've noticed that you can see. And in this case, the first step would be to be able to label the triangle, and you can see that there's more than 2 triangles. We have the triangle ADB, but we also have the triangle ACB. And that's going to be really important because you're going to find this question towards the end of the paper, and you have a right angle, you have some other triangles without right angles, so you're going to know that it's going to be a complex problem that's going to involve some trigonometry, therefore the labelling is really important. The second thing that you can start to do before you start the real problem is to calculate some of the missing angles. So you can see here immediately that we have a right angle triangle with A, B and D. So you know that that one there is 90. You can then find out your missing angle here. You can use your 90 on the bigger triangle. You can find the 180, the missing angle here. So I do that before I start thinking about anything more complicated. So if you can just look at the screen and check that you've also found the 4 missing angles in this triangle. So having these missing angles now calculated, they're going to help you for the various stages of the problem. The first triangle we're going to look at is the triangle A, D and C. That's the non-right angle triangle. When we have non-right angle triangles, we must be applying the sine and cosine rule. You'll see here that I've added the 10 up in the corner here by the angle A, and down here 138. They were calculated on the previous slide with the working out, so make sure you've got those before proceeding. You also have a length given here, 15. So we have all 3 angles and 1 length. Let me remind you here about which rule to use. I've copied the notes from our first page so that we can see which one is most appropriate. The cosine one with 3 sides is obviously not going to work because we only know 1 side, so that one can be crossed off already. The other cosine rule requires 2 lengths. Remember the ones with the 2 sides and the enclosed angle. That's also not going to work. So it's going to be sine. But let's double check. Do we have 2 angles and a side? We have 3 angles and a side, so yes. The other one is not appropriate, but it still doesn't mean that we can't use the sine rule. This one asks for 2 sides and a non-included angle. At the moment, we only have 1 side. So this is the reason why we're using the sine rule. And we can use the sine rule to find this length here. We've got our rule. we write out our rule. We're finding a length, so remember that A and B is on the top and the sine A and the sine B is on the bottom. By substituting in, we can then see on the screen we have 15 divided by sine 10. 15 and sine 10, 15 corresponds with the A, the angle there with 10. The B part here, we're trying to find. It says C on my diagram, but I changed it because it doesn't matter, again, what your angles are. So this one we're looking at here to B, but they're the corresponding. It's the missing angle with the 32. That's why we have x divided by sine 32. We substitute this into the calculator, or rearrange, substitute it into the calculator, and we're left with x equals 45.8 metres. And that's the length here, x, which is AD. So we've now found the length AD, which is 45.8. Now that's not the length we're trying to find. We need to find the height of the tower, which is the perpendicular height. However, this is one step closer. If you look on the next page here, I've now just got the section that I'm interested in. I did that on the last slide as well, and that's another important point when you're problem solving, to just focus on the area of the diagram or the information that you need. You'll now see that we have our angle of 42, and we just have the triangle ABD. And we have our side here that we've just calculated, 45.8. And we want to find x. And that's the length AB. This time we have a right angle triangle. Now you're going to have to take a step back and remember what you do when you've got a right angle triangle. And in this question we have to apply trigonometry, but right angle trigonometry, the one where we use SOHCAHTOA. So in this case we're going to have our triangle and we're going to have to label up the triangle. So we have our right angle, opposite, hypotenuse. We then have our angle of 42. The side opposite the angle of 42 is called O for opposite. And our third remaining side is A, adjacent. In this example, the sides we're interested in is H, because we have it, and O, because we're trying to find it. So you'll remember from SOHCAHTOA that the part we're going to use is the sine part, the SOH. And that tells us that sine x is equal to the opposite side divided by the hypotenuse. If we substitute in our values here, we have sine 42. That's our angle that's involved. Equals opposite. We don't know the opposite side. That's what we're trying to find. So that's x divided by the hypotenuse, which is 45.8. Now, we need to find x on its own. So we rearrange, we multiply this together. So we have 45.8, that's our length of the hypotenuse, multiplied by sine 42. And that's equal to 30.64618,177. Again, you're likely to have to round that to 3 significant figures, so 30.6. Is that a reasonable answer? Well, the hypotenuse is larger, 45.8. We'd expect it to be larger. It's smaller, but not significantly smaller. So yes, that's approximately the right answer. So in that question, we had some angle rules to start with. We then had our sine and cosine rule. In the particular example, we used the sine rule. And then at the end, it went back to a B grade topic, which was the trigonometry for right angle triangles. So all of those things in the same question make it quite complex. So if you've got to the end of that question, well done, and we're going to move on now. So our final section is on the area of a triangle. You'll probably recognise the 2 triangles I've placed here on the screen. They have a height and a base, a perpendicular height. That's a height that's at 90 degrees with the base. And to find the area of these triangles, you simply multiply the height with the base and then divide by 2. That's something that we're all very familiar with. However, we might be given a triangle like this, where there's no perpendicular height. And in this case, the area of a triangle is equal to half the product, that's multiplied, of the 2 sides and the sine of the included angle. Which basically means you need 2 sides and an included angle. So here we have A and B, and we have an included angle here, which is labelled at C. and it's going to be sine c. Again, this formula is on the formula sheet. It says the area of the triangle ABC is equal to half multiplied by AB, that's the product of the two sides, AB, multiplied by the sine of the included angle C. So in this case, we need to have this, this, and this. So two sides and an included angle. Very often, these questions are attached as part B's to sine and cosine rule questions. Let's have a look at how we actually use the formula. So this is an example of a triangle. We have our two sides, 9 and 5, and our included angle of 70. We're going to use our formula, and we're going to have this angle as our C part. So again, I relabel my triangle as C and call that one A and that one B. So I know that this side is lowercase a, this side is lowercase b, and my angle here is 70. So I have two sides and an included angle. So to find the area, I do half, always half, multiplied by the two sides, 5 times 9, multiplied by the sine of the included angle, 70. So half stays the same. You multiply by the two sides and then multiply by the sine of the included angle. Once you've got that, it's simple. You type it into your calculator. So at the same time, a half multiplied by 5 multiplied by 9 multiplied by sine 70 is equal to 21.14308,397. Again, rounded to three significant figures, 21.1 centimetres squared, because we're dealing with area. So the key thing is identifying which two sides and where the enclosed angle is, and then substituting in to find the answer. So there's three triangles for you to try. For each one of them, you need to find the area. I'm going to give you 5 minutes, off you go. Let's have a look at the three questions. Up on the screen is the working out for each of the three. They're all a little bit different. Let's look at the first one. The first one, we have our two sides, 2.4 and 2.8, and our enclosed angle of 54. So this one, we just use the simple formula, half times A times B times sine 54, which is the enclosed angle. And you get the answer, 2.72 metres squared. The second one, we have to use Pythagoras first. We're missing this angle here. So we find Pythagoras, and we find that this length is 97.25. We then find the area just by doing the regular height times base divided by 2. So we have height 72, base 97, multiplied by a half, and we have our area here 3501 centimetres squared. Our third example here, you need to find the enclosed angle. So we have our two sides, 18 and 14, but this angle is the sine angle that we need to be able to use the formula. So we must add our two other angles together, 130 and 22. Subtract that from 180 and we get 28. That can then be used in the formula. We have half multiplied by 18 multiplied by 14. They're the two sides, and the enclosed angle sine 28, which gives us an area of 59.2 centimetres squared. So now it's time for you to take a further assessment on shape, which will be covering the vectors, the sine and cosine rule, and the area of the triangle. Press pause, you have 10 minutes, good luck.